Hello there, and welcome to Life Beyond Seen, where curiosity drifts slowly through the currents of deep time and science becomes a quiet companion for the night. Tonight, we're not just gazing at stars or ticking clocks, we're sinking beneath waves that no longer exist, into oceans that shimmered long before humans ever dreamed of maps. This is a story about a forgotten world, one that came before the dinosaurs we know so well, before the thunder of footsteps on land, before the great beasts of later ages learned to roar. Down in the ancient seas, long before whales sang or sharks took their familiar forms, there was an age of monsters that few remember. An age when the ocean itself was experimenting with what life could become, the Triassic period. If you're listening from somewhere quiet tonight, perhaps the sound of distant traffic, the hum of your room, or the faint rhythm of your own breath could be the sea for a while. Let your imagination fill it with ripples and pale sunlight breaking through blue-green depths. Picture a planet still recovering from near-death. Because that's what Earth was at the start of the Triassic, a world that had nearly emptied itself of life. It was a planet trying again. And somewhere in those new waters, the first strange swimmers began to move. Where are you listening from tonight? Somewhere near a coast, perhaps? Or far inland where the idea of an ocean feels like a memory from another life? It's strange to think that no matter where we stand now, whether in city or desert or mountain valley, that place was once underwater. Every rock underfoot was shaped by the pulse of ancient seas. Every grain of sand was once the shell of something alive. So in a way, we're all children of oceans that vanished long before names or nations. If you find these wanderings soothing or just a comforting background while you drift towards sleep, I'd be grateful if you left a like or maybe subscribed. It helps this little corner of calm reach others who might enjoy taking a slow dive into the past. But for now, just let your thoughts slow. You don't need to keep track of minutes. The surface world can wait. We're going under. Imagine the world 252 million years ago. The continents weren't scattered across the globe as they are today. They were fused into one vast supercontinent called Pangaea, a colossal mass stretching from pole to pole surrounded by an equally immense ocean called Panthalassa. Around its edges lay smaller seas, shallow, warm and teeming with opportunity. But only just. Because the Triassic didn't begin with life, it began with silence. The event that marked its start, the Permian extinction, had wiped out about 90% of all marine species. Coral reefs dissolved. Whole families of fish disappeared. The ocean floors became barren. For a time, even the chemistry of the water turned hostile. When the planet finally began to heal, life didn't return as it had been. The old rulers were gone, leaving the stage empty for new forms to appear. It's one of those quiet truths of evolution that when catastrophe strikes, what follows isn't just loss, but invention. The Triassic seas were a vast experiment, and the creatures that rose within them looked like drafts from a mine testing its range. They were part fish, part reptile, part mystery. The air above those seas was heavy with volcanic haze. The sun burned hotter because the atmosphere held more carbon dioxide than ours does now. The climate was extreme, dry on land, warm in the water. Yet those same conditions created vast shallow basins where sunlight could reach the seabed, warming it just enough for algae and plankton to bloom again. And where there is plankton, there is hope. Tiny crustaceans followed, then small fish, and soon the food web began to weave itself anew. Along the coasts of Pangaea, where rivers poured minerals and nutrients into the shallows, reptiles that had survived the extinction began to wander near the waves. Some hunted along the tide lines, snapping at small fish stranded in pools. Over generations, they grew more adapted to the water. Their legs flattened into paddles. Their lungs became stronger, their bones lighter. In the long patience of evolution, they crossed the threshold between land and sea. These were the ancestors of the first true marine reptiles, the creatures that would soon rule the oceans as completely as their later cousins ruled the land. But the Triassic Ocean was not yet a gentle place to live. Its chemistry fluctuated wildly. In some regions, oxygen levels dropped so low that only specialized creatures could survive. In others, the water was almost too warm to hold enough gas for life at all. Storms were frequent and violent, driven by temperature contrast between the massive continent and the vast ocean surrounding it. Yet in that chaos, evolution thrived. The organisms that adapted to survive such instability became some of the most resilient in Earth's history. To imagine the world of the Triassic, it helps to picture not the calm blue of modern seas, but something more vivid and strange. The waters near the surface glowed with microscopic life, green and gold with phytoplankton. The coastlines were raw and volcanic, black rock meeting restless surf. Where today you might see coral reefs, then there were sponge fields and clusters of shellfish clinging to stone. Farther offshore, the depths dropped sharply, disappearing into darkness. And somewhere down there, something new was learning to swim fast. The first of these new swimmers were small, sleek reptiles with long bodies and delicate limbs that acted as flippers. They hunted fish and squid-like creatures called belemnites. They had sharp, conical teeth, perfect for gripping slippery prey. Their eyes were large, adapted to dim light, and their lungs allowed them to dive deep before returning to the surface to breathe. These were the earliest ichthyosaurs, the so-called fish lizards, though they were neither fish nor lizards. They were reptiles that had returned to the sea, reinventing their bodies for a new kind of life. At first, they still looked awkwardly in between, with long tails and limbs that hinted at land ancestry. But soon, evolution streamlined them into torpedo shapes, tails bending into vertical fins, limbs turning into precise paddles. Within a few million years, they became the undisputed masters of open water. Sleek, fast, and graceful, they hunted in packs, pursued prey across wide distances, and gave birth to live young in the safety of the ocean depths. The Triassic seas were theirs, but they weren't alone. Along the continental shelves, other reptiles were trying different strategies. Some remained near the surface, using their long necks to snap at fish, while keeping their bodies hidden in the shallows. These were the nothosaurs, slender, flexible hunters that slid through the water like eels, but could still haul themselves onto land to rest. Their world was one of lagoons and tidal flats, where the air shimmered with heat, and the smell of salt and decay hung thick. Nothosaurs were among the first to show that the ocean could be both home and hunting ground, a dual existence that hinted at later, more specialized descendants. It's easy to think of these creatures as monsters, and in a sense they were, but not monsters in the way of nightmares. They were the inevitable outcome of life reasserting itself, filling every empty niche left by extinction. In their sharp teeth and curious eyes, in the rhythm of their swimming and the shimmer of their scales, they carried the memory of survival. Every motion was a continuation of a story that had almost ended. The ocean around them teemed with ammonites, spiral-shelled relatives of modern squids, that drifted and darted in glittering schools. Their shells reflected sunlight like coiled pearls. Some were the size of coins, others as large as dinner plates. They were the foundation of the Triassic marine food chain, and their presence told scientists millions of years later that life had fully recovered. Fossils of these ammonites would become time markers, helping paleontologists date the layers of rock that held the bones of their predators. In the deeper waters, sharks swam too, though they were not yet the dominant hunters they would become later. They were smaller, often outmatched by the speed and agility of the new reptiles. There were also ancient fish with thick, armour-like scales, remnants of even older lineages that had somehow survived the Great Extinction. It was a crowded sea of old and new, each adapting in its own way to a world that was still finding balance. Picture yourself hovering above one of these Triassic reefs, if you can call it that. The water is clear but tinted green from the bloom of algae. Schools of small fish scatter as shadows move above them. A shape glides past, sleek and muscular, with a head shaped like an arrow and eyes that seem too large for its body. It turns slightly, revealing a flash of silver scales before vanishing into the haze. Moments later, a smaller creature bursts from the rocks, twisting its long neck toward a darting fish. The jaws snap shut and the ripples fade. Silence returns. The sea breathes again. These moments, if you could have witnessed them, would seem slow and deliberate compared to the frantic life of modern oceans, but they were no less fierce. Every movement mattered. Every heartbeat was a calculation in survival. Evolution was in full swing, sculpting bodies that would define marine life for millions of years. And yet, above these ancient seas, the world was also changing. Forests of conifers and cycads spread across Pangaea's coasts. Insects buzzed in thick swarms. The air, though heavy and warm, carried the scent of resin and salt. The land and sea were linked as always, exchanging nutrients, shaping each other's fate. When rivers flooded, they brought sediments rich with minerals into the shallows, feeding plankton blooms that supported the marine reptiles below. In return, storms over the ocean carried moisture inland, sustaining the plants that stabilized the coasts. It was an early example of the delicate balance that still defines Earth's biosphere today. Every fossil found from this time tells part of that story. Bones of ichthyosaurs discovered in Germany and Switzerland show us their streamlined evolution. Skeletons of nothosaurs found in China reveal how widespread they became. In Italy, paleontologists uncovered fossils of a creature so strange that for years they weren't sure how it had lived. A reptile with a neck longer than its body, stretched like a living fishing pole. Its name was Tanis trophaeus, and it looked like something drawn by a child who loved both snakes and giraffes. We'll meet it properly soon. But even its presence in these early layers tells us something important. Life in the Triassic was not cautious. It was bold, bizarre, and endlessly inventive. For scientists studying these ancient seas, the Triassic is a bridge. It connects the devastated world of the Permian to the lush, dinosaur-filled landscapes of the Jurassic. Without it, evolution's recovery story would be incomplete. The oceans were the testing ground, the laboratory where life learned to rebuild after its greatest fall. Every successful adaptation in the Triassic laid the foundation for what came after. The great marine reptiles of the Jurassic, the flying pterosaurs, even indirectly, the mammals that would one day walk on land again. If you listen closely, you can almost imagine the sound of that ocean. Not the crashing waves of our coasts, but a steady hum, the whisper of ancient tides moving against unfamiliar shores. The world was quieter then, but in that quiet there was potential. Every current carried larvae, spores, and the promise of new beginnings. So tonight, as we drift through this ancient water, we'll follow that promise. We'll meet the creatures that rose from extinction's shadow, the ones that turned emptiness into abundance. The Triassic seas were not kind, but they were generous to those who adapted. The monsters that ruled them were not villains, they were pioneers. The surface above us fades now, replaced by the deepening blue of the open ocean. Somewhere in that twilight zone, an ichthyosaur glides by, its body built for speed, its lungs filled with the same air that once brushed the tops of primitive pine forests. It exhales a faint bubble trail and vanishes again into the dark. Another world entirely, yet somehow still ours. And that's where our dive begins, in a sea reborn, a planet healing itself, and life daring once more to take strange and wonderful shapes. The silence after catastrophe is never empty. It's full of echoes that take time to fade. When the Permian extinction ended, Earth stood on the edge of recovery but didn't yet know how to begin. Almost everything that had once lived in the sea was gone. Coral reefs that had built cities of colour for hundreds of millions of years crumbled into dust. The great schools of fish that had filled the waters vanished. Even microscopic plankton, the The quiet architects of the food chain nearly disappeared. The oceans had turned toxic, heavy with carbon dioxide and hydrogen sulfide, suffocating what little life remained. It was as if the planet had pressed a reset button and left the screen blank. For millions of years afterward, the seas were slow to heal. The sun still rose and set over waves, but those waves rolled across a thin, barren film of life. Bacteria floated in the shallows, feeding on minerals instead of light. Algae struggled to gain a foothold. Small creatures, adapted to the harsh new chemistry, tried to rebuild from nothing. The water itself was warm, sometimes too warm, because the atmosphere held more carbon dioxide than modern humans could imagine. Volcanoes had poured it out for centuries, clouding the skies and changing the balance of gases the planet relied on. And yet, despite that chaos, life didn't stop. It waited, adjusting one molecule at a time until the oceans could breathe again. Imagine standing on the shore of that world, if standing were possible. The coastlines of Pangaea were not gentle beaches of sand, but rough stretches of dark rock and mud. Steam hissed from cracks where magma met seawater. The air smelled faintly of sulphur and salt. The horizon was vast, a single ocean wrapping the planet. Somewhere beyond it, distant storms brewed, pushing waves that could travel for weeks before meeting land again. It was a harsh place, but not lifeless. In tide pools and estuaries, new organisms were finding their way. The world was beginning again in miniature. Scientists studying the layers of rock from this time can see the signs of that slow return. The sediments tell a story of chemistry changing back toward balance. Carbon levels dropped bit by bit. Oxygen began to rise in deeper layers. In those layers, fossils appear, not many at first, just scattered traces. Shell fragments, the faint impressions of burrows, the marks of tiny creatures testing the seabed. Each of those marks meant something enormous. Survival had restarted. Among the first to reappear were the ammonites. Their ancestors had nearly died out, but a few lineages endured. They multiplied quickly, their coiled shells becoming more diverse and intricate as they adapted to new niches. They were small at first, fragile, but they spread fast. Ammonites became symbols of resilience, the spiral shape repeating across millions of years, marking each step of the ocean's recovery. Around them, new kinds of plankton began to bloom, restoring the base of the food web. These invisible drifters changed everything. With plankton came small fish and filter feeders. With fish came predators. The early Triassic Ocean was a world in transition. It had no established order yet, no dominant species. Everything was still trying to figure out what worked. That made it unstable but also incredibly creative in evolutionary terms. In this laboratory of survival, lineages experimented wildly. Fish developed new forms of armor and fins. Crustaceans found new ways to filter food from the water. Reptiles, having survived on land, began to take an interest in the water's edge. Life was improvising, and every mutation that helped something move, breathe, or hunt a little better had a chance to thrive. If we could watch this slow rebirth unfold, we'd see landscapes and seascapes unlike anything today. The shallow basins of the Tethys Sea stretched between what are now Africa, Asia, and Europe. They were cradles of recovery, warm, nutrient-rich, and constantly reshaped by shifting tectonic plates. Earth's crust was restless after the stress of the extinction. Volcanoes erupted often, spewing not just lava but minerals that fertilized coastal waters. Rain washed those nutrients into the sea, triggering blooms of life. The process was violent but productive. From death came food, and from food came the slow resurgence of ecosystems. One of the most fascinating parts of this era is how quickly life adapted once it gained a foothold. Evolution, when conditions allowed it, seemed almost impatient. Species diversified at an incredible rate, filling every niche left vacant by the catastrophe. Within a few million years, entire communities had reassembled themselves. They weren't the same as before, but they worked. Coral-like organisms reappeared, building small reefs. Fish developed new jaw structures suited for new prey. Even plankton species showed complex diversification, creating the foundation for the food webs we recognise today. And yet, the memory of extinction lingered in the chemistry of the ocean. Even as life recovered, oxygen levels fluctuated dangerously. In some regions, the deeper water remained anoxic, deprived of oxygen for millions of years. Anything that swam too deep suffocated. This forced most marine life to stay near the surface, where sunlight and wind kept the water mixed and breathable. It created a world of crowded shallows, where predators and prey constantly crossed paths. Survival here meant speed, agility, and sharp senses. The stage was being set for the arrival of the great marine reptiles that would define the rest of the Triassic. The first steps toward that transformation came from creatures that lived at the edges of the sea. Some reptiles that had survived the extinction were semi-aquatic. They hunted fish along riverbanks or scavenged carcasses washed ashore. Over generations, their bodies changed subtly. Limbs flattened, tails grew stronger, and lungs adapted for longer dives. These were slow, small changes, but over time they turned land dwellers into swimmers. Evolution doesn't move with intent, it moves with opportunity. The ocean offered safety, food, and space. Land had become harsh, often dry and unpredictable. For some reptiles, water wasn't just a refuge, it was the future. When fossils of these transitional creatures are found, paleontologists can see the story written in bone. The structure of the limbs shows how they shifted from walking to paddling. The ribs expanded, suggesting lungs capable of deeper breaths. The skulls became more streamlined, the eyes moving to positions better suited for hunting underwater. Each adaptation was a small adjustment, but together they formed the blueprint for entirely new ways of living. The creatures that followed took those changes further. They became the first true marine reptiles, animals fully adapted to ocean life. Among them were the ichthyosaurs, sleek swimmers that would soon dominate the open seas, and the nothosaurs, long-necked hunters of coastal waters. They didn't appear overnight. Their evolution stretched over millions of years. But when they did emerge, they filled the oceans with energy and motion once again. It's hard to convey how alien the world must have looked then. Imagine standing on a cliff overlooking one of these early Triassic seas. The light would be sharper, the air heavy with heat. Below you'd see schools of fish flashing silver in the sunlight, their shapes strange and primitive. Beyond them, long shadows moved, reptilian bodies twisting and gliding with deliberate grace. They weren't dinosaurs, though they lived alongside their early relatives on land. They were something else entirely, born of a different experiment. The ocean was their world, and they were learning to master it. One of the most remarkable things about this age is how it marked a turning point for Earth's ecosystems. Before the Permian extinction, the oceans had been dominated by invertebrates, creatures like trilobites, brachiopods, and corals. Afterward, the balance shifted toward vertebrates. Fish, reptiles, and other creatures with backbones began to take over. It was the beginning of a new kind of marine hierarchy, one that would eventually lead to the great oceanic predators of later ages. The Triassic was a time when the rules of life were rewritten. Scientists can trace this transformation in the fossil record. In rock layers from the early Triassic, diversity is low, species are small, and the food chains are simple. As time progresses, the layers change. Shells become more varied, bones more complex, and predator fossils more frequent. By the Middle Triassic, the evidence shows thriving ecosystems, reefs, schools of fish, apex predators. It's as if the planet exhaled after holding its breath for millions of years. But recovery wasn't smooth. There were setbacks, periods when the oceans became oxygen poor again, causing smaller die-offs. Each time, life recovered a little differently, testing new forms and strategies. It's these cycles of destruction and renewal that shaped the unique diversity of the Triassic world. Nothing was stable for long, so adaptability became the key to success. In that constant flux, one group of creatures emerged that would define the ocean for tens of millions of years. They started small and tentative, but soon became swift and specialized. They hunted fish and cephalopods, gave birth to live young, and dominated every depth they reached. These were the ichthyosaurs, the fish lizards, and they embodied everything the Triassic stood for: resilience, innovation, and the beauty of adaptation. Their rise marked the moment the ocean truly came alive again. The ichthyosaur's story is remarkable not just for its biology, but for what it represents. When scientists find their fossils, they often find them in positions that look peaceful, curved as if gliding. Some even show embryos inside their bodies, frozen in stone as proof that these reptiles gave birth at sea. It's a detail that connects them to mammals millions of years later, showing how different branches of life sometimes find similar solutions. Giving birth in water freed them from land forever. It meant they could live their entire lives in the sea, independent of the shores that had first nurtured them. Meanwhile, in shallower regions, the nothosaurs were carving out their own path. They didn't have the speed of ichthyosaurs, but they had flexibility and stealth. With their long necks and needle-like teeth, they could strike at fish with precision. They swam with slow, deliberate movements, conserving energy in the calm lagoons and coastal shallows. Some scientists believe they hunted in groups, herding prey toward the surface. Whether that's true or not, their fossils suggest social behaviour, something rare and remarkable for reptiles of that age. It's easy, looking back, to see these animals as inevitable products of evolution, but nothing about their survival was guaranteed. Each generation faced an unstable planet, unpredictable climates, and shifting coastlines. Volcanic eruptions could poison the air for decades. Sea levels rose and fell dramatically, yet life persisted, finding ways to turn each challenge into opportunity. The Triassic oceans became a vast canvas of trial and error, and every creature that thrived did so because it could change faster than the world around it. In time, this resilience reshaped the very chemistry of the sea. The spread of plankton and algae increased oxygen production, stabilizing the upper layers of the ocean. The return of coral-like builders created habitats for smaller species. Predators kept populations in balance, preventing overgrowth and collapse. What began as a fragile experiment became a self-sustaining system. The oceans had healed, not completely, but enough to support abundance again. And with that abundance came complexity, ecosystems layered from surface to seabed, each level connected to the next. The Triassic world was no longer silent. The water thrummed with motion, the steady rhythm of fins and the flicker of scales. The balance of life had returned, and with it, the foundation for everything that followed. Above these seas, the continents were still dry and vast, dotted with forests of early conifers. The air was hot and thin. But the oceans told a different story. Beneath their surface, life had not just survived, it had reinvented itself. The stage was ready for the rise of the true oceanic monarchs, the reptiles that would dominate for the next 50 million years. The dawn after darkness had come. The world had remembered how to live again, and in the depths, evolution was waiting to reveal its next creation. When the first reptiles ventured toward the waves, the world must have seemed enormous again. The land was still recovering from its own scars, forests of conifers and cycads spreading across the dry supercontinent of Pangaea, but it was the oceans that held the most potential. Food was plentiful, competition was low, and the ancient instincts that drove life to explore found their next great frontier beneath the surface of the sea. These first tentative reptiles at the water's edge could not have known that they were about to begin one of evolution's most ambitious experiments, turning creatures built for solid ground into the masters of a liquid world. It started with curiosity, or something that functioned like it. Along the coastal margins of the Tethys Sea, small reptiles hunted among the tidal pools. They fed on stranded fish, crustaceans and carrion washed in from the shallows. Each generation that lingered a little longer near the water discovered advantages. The ocean offered escape from land predators, an endless buffet of small animals, and a stable climate compared to the extremes of the Triassic deserts. Over time, the traits that made these hunts easier, stronger tails, flatter limbs, larger lungs, became more common. Nature was making adjustments in slow motion, sculpting bodies that could move more efficiently through water. One of the earliest known examples of this transition is found in the fossil of a small reptile called Utatsusaurus. Discovered in Japan and dating back to the early Triassic, it shows a creature caught halfway between two worlds. Its body was long and slender, its limbs still recognizable as legs but already modified into paddles. It had a powerful tail that helped it propel through the shallows, though it probably still came ashore to rest or lay eggs. Utatsusaurus might not have looked graceful, but it was a pioneer. From forms like this would evolve the first true marine reptiles, the ichthyosaurs, who would soon take full possession of the open sea. The path from land reptile to oceanic hunter was not a straight line. It branched, doubled back, and experimented in many directions at once. Some groups, like the nothosaurs, stayed close to shore, hunting in lagoons and estuaries, their bodies built for both swimming and crawling. Others, like the ancestors of ichthyosaurs, abandoned the land almost entirely. The fossil record shows that this transition happened relatively quickly, perhaps over just a few million years, a blink by geological standards. It was as if the ocean, left vacant after the extinction, invited innovation, and evolution accepted the invitation with enthusiasm. These early marine reptiles didn't look like the sleek hydrodynamic forms that would come later. They were awkwardly built, with elongated bodies and flexible spines. Their limbs a compromise between legs and fins, but they were efficient enough to survive and reproduce, and that was all evolution needed to keep refining the design. The pressures of the marine environment, buoyancy, drag, oxygen limits, and the need to pursue prey guided each adaptation. Over time, bodies became more streamlined, tails more muscular, and limbs more specialized for propulsion. It's fascinating to imagine how these creatures moved. Early nothosaurs probably swam in a sinuous motion, their bodies undulating like those of modern seals or otters. They could twist through coral growths and ambush fish in narrow spaces. Their long necks and small heads gave them reach without requiring full body movement, conserving energy in the dense medium of water. Ichthyosaurs, on the other hand, took a different route. Their descendants would eventually develop crescent-shaped tails and rigid dolphin-like bodies built for endurance swimming. But in these first stages they relied more on whole-body undulation, moving like eels rather than whales. Each generation became a little faster, a little stronger, a little more aquatic. The Triassic seas offered plenty of motivation for such innovation. After the mass extinction, new ecosystems were forming, full of opportunities for predators willing to adapt. Small fish and squid-like cephalopods flourished in the nutrient-rich shallows, feeding on the explosion of plankton. Those fish in turn attracted hunters. Competition on land was fierce, but in the water the stage was wide open. The reptiles that took to the sea faced few serious rivals. They were free to experiment, and the result was an astonishing burst of diversity. Fossil beds from places like Monte San Giorgio in Switzerland, the Germanic Basin, and parts of China preserve entire communities of these early marine reptiles. The bones tell a story of rapid evolution and global spread. Within a few million years of their first appearance, these creatures had colonized nearly every warm coastal region on Earth. Some remained small, less than a meter long, gliding among reefs. Others grew larger, with streamlined torsos and broad fin-like limbs. Their skulls evolved specialized jaws, some long and narrow for catching slippery fish, others short and powerful for crushing shells. It was an arms race of design, and the oceans were the testing ground. One of the key challenges of moving from land to sea is breathing. Reptiles are air breathers, and adapting to a life underwater required efficient lungs and control over buoyancy. Fossil evidence shows that marine reptiles developed larger chest cavities to hold greater volumes of air. Some species evolved dense bones, helping them sink and maintain stability near the sea floor, while others developed lighter skeletons that made surface swimming easier. Even their skin began to change, becoming smoother and more hydrodynamic. Step by step, trait by trait, evolution transformed them into creatures perfectly suited for their new environment. What makes this transition so remarkable is that it happened multiple times independently. Ichthyosaurs, nothosaurs, placodonts, and later plesiosaurs and thalatosaurs all evolved from different reptilian ancestors, yet each found its own way to conquer the ocean. This pattern of convergence, different lineages arriving at similar solutions, reveals how consistent the pressures of marine life are. The ocean demands certain shapes, certain efficiencies. To swim fast, you must be streamlined. To catch fish, you need precision. To survive, you must balance power with endurance. No matter where evolution starts, the sea shapes its children in similar ways. Placodonts, for example, took a very different path from ichthyosaurs. Instead of becoming swift hunters, they became armoured grazers, feeding on shellfish along the seafloor. Their bodies were squat and heavy, their teeth flattened into crushing plates. Some developed bony shells resembling those of modern turtles, though they weren't directly related. They moved slowly, using their strong limbs to push along the bottom, crunching through mollusks and leaving trails of broken shells behind them. In their own way, they were just as specialised as the faster predators. The Triassic Ocean had room for all of them: hunters, scavengers, grazers and opportunists. As these groups diversified, so did the ecosystems around them. Reefs began to rebuild, hosting a wide array of invertebrates. Ammonites grew in size and complexity, becoming a staple food source for marine reptiles. New kinds of fish appeared, their scales thinner and their swimming styles more agile, allowing them to escape predation. The arms race continued, and with every new prey, adaptation came a predator designed to counter it. The ocean was no longer recovering, it was thriving. Scientists studying the Triassic often marvel at how fast this transformation occurred. From near total collapse to thriving ecosystems in less than 10 million years is a breathtaking pace by evolutionary standards. It's as if life, once pushed to the brink, rebounded with a vengeance. The diversity of marine reptiles exploded, and their fossils appear in every corner of the ancient world. Some even adapted to freshwater or brackish environments, showing just how versatile they had become. In many ways, the rise of the marine reptiles mirrored what was happening on land. Dinosaurs were beginning their own ascent, filling the empty niches left by earlier extinction. But while dinosaurs would dominate the continents, the seas belonged to the reptiles that had chosen the water. Their success reshaped marine ecosystems permanently. They introduced new forms of predation, new balances of energy, and new evolutionary pressures that would influence marine life for millions of years. If you could look at the Triassic Ocean from above, it would seem both familiar and alien. The surface sparkled under a sun that was slightly harsher than ours. Beneath, schools of fish darted through clear water, their scales flashing in bursts of silver and gold. Shadows moved among them, long sleek shapes gliding effortlessly. Near the coast, smaller reptiles ambushed prey from behind rocks and coral. In deeper water, larger forms cruised with slow, confident strokes. The rhythm of life had returned, and it pulsed with energy. The bones of these creatures preserved in rock reveal details that bring them to life. In some fossils, the outlines of skin and muscle are visible, showing how their bodies were shaped for hydrodynamics. In others, embryos lie within the body cavities, evidence of live birth in the water. Some specimens even contain fossilized stomach contents. Fish bones, ammonite shells, the remains of smaller reptiles, proof of their diets and hunting behaviours. It's through these traces that scientists can reconstruct not just their anatomy, but their lives. The ichthyosaurs in particular show an extraordinary degree of adaptation. Their eyes grew enormous, some as large as dinner plates, allowing them to hunt in dim light or at great depths. Their vertebrae formed flexible columns that powered strong sweeping tails. Their skin, preserved in a few rare fossils, shows no sign of scales, smooth and rubbery like that of modern dolphins. They were reptiles, but they looked and moved like mammals. Evolution had, in a sense, reinvented the whale 200 million years early. Each of these traits, streamlining, large eyes, smooth skin, represents a solution to the challenges of marine life. The fact that similar adaptations appear again later in unrelated groups like whales and seals is a reminder of how nature often repeats itself when faced with the same problems. The Triassic marine reptiles were not just products of their time, they were prototypes for future oceanic life. As impressive as these creatures were, they lived in a world that was still unstable. The Triassic climate was marked by extremes. Sea levels fluctuated, temperatures swung between hot and hotter, and volcanic activity remained frequent. Each generation had to adapt not just to predators and prey, but to a planet still settling into its new rhythm. Yet somehow, these challenges made them stronger. Species that survived these swings became incredibly resilient, capable of thriving in a wide range of conditions. It's one reason why marine reptiles became so successful. They were built to handle change. This adaptability extended beyond physiology. Their reproductive strategies evolved too. Laying eggs on land limited how far from shore a species could travel. Giving birth in the water freed them from that restriction. Fossils showing ichthyosaurs in the act of live birth, embryos emerging tail first, are among the most evocative in paleontology. They capture a moment of life and death suspended in stone, a mother ensuring the survival of her kind in the only world she knew. It's an image that transcends species and time, a quiet echo of continuity in a world that had nearly lost it. By the Middle Triassic, marine reptiles had established themselves as the dominant vertebrates of the sea. They filled every available niche, from fast-moving predators to slow, armoured grazers. Their presence shaped ecosystems and influenced the evolution of other marine life. They were the ocean's engineers, the architects of a new balance. The era of the marine reptiles had truly begun. If we could drift among them now, in those long-vanished waters, we might be struck by how alive everything felt. The sea would hum with movement, every ripple carrying the pulse of an ecosystem reborn, and somewhere in that expanse, a young ichthyosaur would break the surface for air, its sleek head glistening in the Triassic sun before diving again into the depths. The air it breathed would one day nourish forests. The carbon it exhaled would one day become stone, but for now it belonged entirely to the ocean. The birth of the marine reptiles was more than an evolutionary event. It was the ocean remembering how to dream. It was the planet writing a new chapter of life not in forests or plains, but in water. The Triassic seas, once barren and silent, now thrummed with hunters, grazers and explorers. The reptiles had claimed them, and they would hold them for tens of millions of years. The experiment that began with curiosity at the tideline had succeeded beyond all measure, and beneath the rippling surface the next stage of that story was already unfolding, as these creatures learned not just to survive, but to rule. The seas that the first marine reptiles inherited were not like the oceans we know today. Their waters were warmer, their chemistry unstable, and their geography entirely alien. When we imagine oceans, we think of continents separated by blue vastness. But in the Triassic, the world was largely united under one colossal landmass called Pangaea. It was an expanse so large that it created its own extremes of climate. The interior of this supercontinent baked in relentless heat, while the coasts offered narrow ribbons of life where land met sea. Surrounding it all was the immense Panthalassa Ocean, stretching so far that the curvature of the planet itself seemed to cradle it. Within that world-sized ocean lay smaller bodies of water, shallow, warm and enclosed by continental shelves, where most marine reptiles lived and evolved. The most important of these was the Tethys Sea, the glittering heart of Triassic marine life, bordered by the lands that would one day become Africa, Asia, and Europe. To stand beside the Tethys Sea would have been to witness a world in flux. The air shimmered with heat, carrying the scent of resin from forests that grew close to the shoreline. The land sloped gently toward beaches of coarse sand mixed with fragments of ancient coral and shells. Beyond that, the water glowed green and gold beneath a sun unfiltered by polar ice or modern ozone. The climate was global summer, relentless but rich in energy, and that energy drove the rhythm of the seas. Evaporation was high, rainfall unpredictable, and storms frequent. These storms did more than shape coastlines. They churned the surface waters, mixing nutrients that fed the smallest organisms. From the chaos of waves came the abundance of life. At first glance, the Triassic Ocean might have seemed calm, but beneath its surface was a busy and competitive world. Plankton drifted in vast clouds, invisible to the naked eye but forming the foundation of everything above them. They were the planet's quiet chemists, capturing sunlight and turning it into energy. Small fish and crustaceans grazed on them, forming dense schools that shimmered in the shallows. Over time, these schools became the heartbeat of the sea, feeding the reptiles, sharks, and larger fish that followed. Each layer of life fed the next, from the microscopic to the monstrous, all linked in an unbroken web. The geography of the ocean floor played a major role in shaping this world. Where tectonic plates met, volcanic ridges rose, creating chains of islands that broke the waves and formed protected lagoons. These sheltered environments became nurseries for young marine reptiles and hatcheries for fish. The warm, shallow basins near the coasts were especially productive, rich with algae, sponges, and early coral-like organisms. Fossil evidence suggests that these environments were dotted with reef systems, not the bright coral reefs we picture today, but structures built by sponges and microbial mats, ancient frameworks that offered both shelter and ambush points. Here, creatures like nothosaurs hunted, using the cover to sneak upon shoals of fish or ammonites gliding past. In deeper water, beyond the reach of sunlight, the ocean turned dark and still. Oxygen levels dropped sharply there, creating vast regions where little could survive. These anoxic zones were a legacy of the world's earlier instability. They formed natural boundaries, dividing ecosystems into layers. Most marine reptiles stayed near the surface, where they could breathe and hunt, but some species likely dived deep for short periods in pursuit of prey. Ichthyosaurs, with their powerful tails and large eyes, were among the few capable of venturing into those twilight depths, chasing squid-like cephalopods through the dim blue gloom. The chemistry of these waters tells its own story. During the Triassic, the concentration of dissolved carbon dioxide in the oceans was high, and temperatures hovered well above modern averages. Some regions were nearly tropical from pole to pole. The polar ice caps, if they existed at all, were minimal. That warmth created stable layers of water that didn't mix easily, which helped maintain those oxygen-poor depths, but also made surface life incredibly productive. In the bright shallows, the sun's energy poured directly into the food chain, feeding blooms of plankton that turned the water a hazy green. To creatures like the ichthyosaurs gliding through it, this world must have seemed endless and abundant, filled with the constant motion of the life rebuilding itself. Even the sound of this ocean would have been different. Without whales or modern fish that produce low-frequency calls, the Triassic seas would have been quieter, filled instead with the crackle of volcanic vents, the grinding of crustaceans on coral, and the splashes of predators breaking the surface. Perhaps the occasional rumble of an underwater eruption echoed across the shallows, shaking the bones of every creature nearby. It was a quieter kind of vitality, but it was far from peaceful. Life in these waters was a delicate balance between hunger and survival. The light filtering through the surface created a strange kind of beauty. It shifted constantly as currents stirred sediment and plankton, painting the ocean in shades of jade and amber. Schools of ammonites moved like living galaxies, their spiral shells catching the sunlight as they turned. Small fish flickered between them in flashes of silver. Overhead, reptilian hunters cast moving shadows, their sleek bodies reflecting a faint shimmer from the waves above. It was a world of motion, a ballet of evolution where everything depended on the chase. To the marine reptiles, this ocean was both home and battlefield. Each species carved out its niche. The nothosaurs lingered near the coasts, stalking fish among reefs and tidal flats. Their long necks and narrow skulls allowed them to strike with precision, while their limbs, halfway between legs and flippers, let them move gracefully in both water and land. The ichthyosaurs preferred the open sea, where their streamlined bodies gave them an advantage over any other predator. They travelled in groups, perhaps following seasonal migrations of prey across the Tethys currents. Fossil evidence from bone beds suggests they gathered in large numbers, possibly for breeding or hunting, moving together in ways that foreshadowed the social behaviour of dolphins millions of years later. There were also the placodonts, the slow armoured grazers that fed along the sea floor. They moved in herds, their heavy shells clinking softly as they foraged. The Triassic ocean floor was not barren sand, but a mosaic of life. Sea urchins crawled among algae, crinoids waved their feathery arms, and trilobites, once dominant, were now gone, replaced by new arthropods adapted to the changing chemistry. Mollusks of all kinds thrived, from small clams to coiled ammonites. Every square metre of seabed was a struggle for space, a microcosm of evolution's persistence. Above this thriving surface, the atmosphere played its part. The greenhouse world of the Triassic was unstable, with periodic bursts of volcanic activity releasing more carbon dioxide into the air. These outgassings occasionally warmed the oceans further, killing off species that couldn't adapt, but each time recovery followed swiftly. Life seemed almost eager to fill every gap. The interconnectedness of the ocean and atmosphere meant that the fate of marine reptiles was tied to forces far beyond their control. A volcanic eruption on land could alter the currents and chemistry of the sea for centuries. Still, the creatures adapted. Some developed wide ranges, capable of living in different temperature zones. Others specialised, confining themselves to narrow ecological bands where they could outcompete rivals. Even in this warmth, there were seasons, though not as we know them. The tilt of the planet still dictated cycles of sunlight, rainfall and migration. These rhythms shaped behaviour. Marine reptiles may have followed the changing blooms of plankton, just as whales follow krill today. Fossil evidence hints at such movement, species appearing in one region's sediment layers for a few million years and then vanishing as currents shifted. The Triassic world was never static. It pulsed with change. In many ways, it was a world of experiments. The boundary between land and sea was porous, with creatures moving between them. Some reptiles ventured only partly into the water, while others became nearly indistinguishable from fish. Each species was testing what was possible. The Triassic seas were the planet's workshop, a place where evolution tried out designs that would later echo through natural history. The long-necked Tanystropheus, for instance, was one of those experiments, a reptile so bizarre it seemed like a biological riddle. With a neck longer than its body, it may have lived partly in water, waiting motionless before striking at fish near the surface. The sea encouraged such oddities because it offered both space and safety for risk-takers. Scientists can trace the contours of this ancient world through fossils and the chemistry locked inside rocks. By studying isotopes of oxygen and carbon, they can reconstruct temperatures and salinity levels, revealing patterns of change across millions of years. These data show that the Triassic oceans were consistently warm, often exceeding 30 degrees Celsius near the surface. They also show that the concentration of dissolved oxygen was much lower than today's levels, meaning that marine reptiles and fish had to evolve highly efficient respiratory systems to survive. The structure of their bones, light yet strong, shows how they balance buoyancy and strength. Every adaptation written in stone tells us how intimately life was tuned to its environment. It's easy to forget that these creatures lived not in isolation, but as part of vast interconnected systems. The tides carried nutrients from the land into the sea, feeding the growth of plankton that sustained everything else. The death of one species fed another. Carcasses of marine reptiles that sank to the seabed became ecosystems in themselves, attracting scavengers and bacteria. Even decomposition played a role in maintaining balance. The Triassic oceans were alive in every sense, from the surface glittering with sunlight to the murky depths where shadows fed on decay. The colour of the sky above those seas would have been different too. The high levels of volcanic gases and particulates likely tinted it a deeper orange near the horizon, fading to pale gold overhead. Sunsets would have burned with a reddish hue, reflecting off the water and turning the surface into molten light. For creatures that lived there, this was simply the texture of existence. There was no contrast to compare it to, no sense of change, only the endless rhythm of the sea and the heat of the sun. From this environment, the marine reptiles drew everything they needed. Their food, their safety, even their sense of direction came from the ocean's patterns. Currents guided their migrations. The position of the sun helped them navigate. The moon, though perhaps less visible through the haze, still pulled at the tides, shaping coastlines and exposing feeding grounds. Everything was interconnected, everything alive. It's remarkable to think that this world, so distant in time, is preserved in the rocks beneath our feet. The limestone cliffs of Europe, the red deserts of China, and the mountain peaks of the Alps all hold fragments of that vanished ocean. What were once coral beds are now quarries. What were once sandy shores are now stone ridges. Time has folded the world upon itself, but the traces remain. When paleontologists split open a slab of rock and reveal the outline of an ichthyosaur or the spiral of an ammonite, they're not just uncovering fossils, they're reopening a window to this warm ancient sea. For all its strangeness, the Triassic Ocean also holds a reflection of our own world. Its cycles of destruction and renewal mirror the fragility of modern ecosystems. Its periods of warming and recovery remind us how deeply climate and life are intertwined. And its creatures, though long gone, embody the same restless drive to adapt that still defines evolution today. The marine reptiles didn't just inhabit their world, they shaped it, and in doing so they left a legacy that echoes in every modern ocean. Some nights, when scientists study those fossils under lamplight, they can trace the marks of muscle attachments, the shape of flippers, the curve of vertebrae, and almost feel the movement behind them. It's as if the creature is still swimming just out of sight, still part of a living sea that never truly ended. The Triassic Ocean may be gone, but the world it created remains inside every drop of water, every tide, every heartbeat of life that depends on the sea. As the Triassic continued, these oceans would become even more dynamic. Currents would shift, continents would drift, and the creatures that ruled the waves would grow larger and more specialized. The balance of power was changing again, as evolution's experiment gathered momentum. The warm, shallow seas that once cradled fragile beginnings were about to become the stage for some of the fastest, fiercest hunters the planet had ever seen. And somewhere out there, beneath the rippling light, an ichthyosaur's fin sliced through the water, heralding the arrival of a new era in the ocean story. In the warm waters of the Triassic, where sunlight reached deep and the continents still clung together in one great mass, evolution crafted a creature that seemed to fuse grace with precision. Among all the new forms rising from the ocean's recovery, one stood apart, not because it was largest or most fearsome, but because it was perfectly suited to its element. The ichthyosaurs had arrived, and the sea itself seemed to move differently around them. They were not born rulers of the waves, but in time they would become them. Imagine the surface of the ancient Tethys Sea on a windless morning. The air is heavy with heat. the horizon a blur of gold and green. A ripple breaks the surface, just one, then another, like breath stirring the stillness. Moments later, a sleek shape arcs upward, silver blue and glistening. It catches the light for an instant before sliding back beneath the waves. The movement is effortless, smooth, and final, leaving barely a trace. Below that calm surface, entire families of ichthyosaurs glide through the water in silence, their sleek bodies cutting through the currents with the same ease that birds ride the air. They were reptiles by ancestry, but the ocean had reshaped them completely. Their bodies no longer carried the angular stiffness of their land-dwelling cousins. They had become curved, streamlined, almost liquid in form. Long before mammals took to the sea, ichthyosaurs had already perfected the art of marine life. Their skeletons tell the story of that transformation. Elongated snouts filled with conical teeth, vertebrae forming flexible columns, limbs flattened into flippers that could steer with precision. Each piece of anatomy was a solution to the demands of the sea, refined over millions of years until nothing was wasted. Their closest ancestors were small, lizard-like reptiles that had once walked along the Triassic coasts. Over time, as they chased prey deeper into the water, their limbs became less useful for walking and more useful for swimming. The bones shortened and multiplied, forming a structure like a fan. Their tails grew longer and more muscular, eventually bending downward at the tip and developing a vertical fin. That tail would become their engine, driving them forward in smooth, powerful strokes. Evolution had taken the design of a land reptile and reimagined it entirely for life underwater. The result was speed, remarkable speed for its time. Ichthyosaurs could swim faster than any other reptile, rivaling modern dolphins and tuna in efficiency. They moved with the same side-to-side motion seen in fish, their tails slicing through the water with rhythmic precision. Their large eyes, among the biggest of any known vertebrate, allowed them to see in low light, suggesting they hunted not just near the surface, but also in the dim blue depths. Fossilized remains show that the bones surrounding those eyes were reinforced with rings of bone, keeping them from collapsing under the pressure of deep dives. The ichthyosaurs were not merely coastal swimmers, they were masters of the open ocean. What they hunted depended on their size and habitat. Smaller species chased schools of fish and ammonites, darting between them with incredible agility. Larger forms, some over 10 meters long, preyed on other reptiles, sharks, and large cephalopods. Their teeth were built for grip rather than slicing, perfect for catching slippery prey. Fossilized stomach contents reveal entire fish preserved inside their rib cages, showing that digestion began quickly, but capture was clean and efficient. These were not clumsy predators. They were specialists tuned to the rhythm of pursuit and precision. To see them in motion would have been to witness an early masterpiece of design. Their skin, smooth and hydrodynamic, contained no scales. In rare fossils, impressions of soft tissue reveal outlines of dorsal fins and flukes, proving that they looked astonishingly like modern dolphins. Yet they were no mammals. They breathed air through nostrils placed high on their snouts, and they gave birth to live young in the water. Fossil specimens have captured these moments, embryos preserved inside the bodies of mothers, some even in the process of emerging tail first. This detail ensured survival. A head-first birth would risk drowning the newborn before it could reach the surface. Nature had thought of everything. Their intelligence is difficult to measure, but evidence suggests they may have been social. Groups of ichthyosaur fossils found together imply coordinated movement or migration. Perhaps they travelled in pods, communicating through body language or vibrations in the water. Such behaviour would have made sense in the vast openness of their world. Hunting in groups offered advantages, herding schools of fish or driving prey towards shallower waters. It's tempting to imagine that somewhere in those ancient seas, mothers guided their young, teaching them to dive and breathe in patterns that became instinct over generations. The Tethys Sea gave them everything they needed: Its warmth supported their metabolism, and its expanse allowed them to roam freely. Some species became specialists of the open ocean, while others remained near continental shelves. Over time, their bodies adapted to these roles. Shallow water ichthyosaurs developed broader fins for maneuverability, while deep-sea hunters grew longer, narrower bodies for speed and endurance. The diversity within the group was astonishing. At least a dozen genera thrived during the Triassic alone, each slightly different, each an answer to a specific ecological question posed by the sea. The fossil record preserves snapshots of that diversity. In the early Triassic layers, species like Cowhosaurus still carried hints of their terrestrial origins: smaller fins, less developed tails. A few million years later, creatures like Mixosaurus show the transition in full swing. The body streamlined, the tail bent downward into a fin, the limbs transformed into perfect paddles. By the middle Triassic, the ichthyosaurs had reached their peak with forms like Cymbospondylus, massive predators that could reach lengths of 10 meters and dominate any region they entered. Evolution had moved quickly, compressing an entire saga of adaptation into a geological instant. What made them so successful was not just speed, but efficiency. Ichthyosaurs breathed air, but they could stay submerged for long periods thanks to large lung capacity and high blood oxygen storage. Their metabolism was elevated compared to most reptiles, possibly approaching that of warm-blooded animals. This allowed them to maintain steady activity even in cooler waters. In essence, they had begun to bridge the gap between cold-blooded reptiles and the high-performance physiology of later marine mammals. The ocean demanded endurance, and the ichthyosaurs provided it. Scientists studying their fossils can even estimate their swimming styles by analysing muscle attachment points on the bones. The shape of their vertebrae and ribs shows a body built for continuous motion, with strong tail muscles propelling them forward and flexible spines allowing fine control. Unlike fish, which use lateral undulation across the entire body, ichthyosaurs concentrated their power in the tail, keeping the rest of the body relatively rigid. This made them faster and more energy efficient. Every movement was calculated, every curve of the body honed by selection. Their eyes tell another story, one of adaptation to a world of light and darkness. The size of the orbit suggests that some species could see in near darkness, perhaps hunting in deep water during the night, or at depths where sunlight barely reached. This ability would have given them a significant advantage, letting them exploit prey that others couldn't reach. In this way, they claim not just the surface, but the full vertical dimension of the ocean. When we picture the Triassic seas, it's easy to imagine chaos: volcanic islands, shifting currents, unstable climates. But for ichthyosaurs, this chaos was opportunity. Their mobility allowed them to migrate vast distances, following the shifting belts of productivity that moved with the seasons. In a world of extremes, adaptability was survival. Some fossil sites, such as those in Nevada and Germany, reveal remains of individuals that may have travelled hundreds or even thousands of kilometres before death. The oceans were open highways, and these creatures were among the first long-distance travellers in Earth's history. Their dominance lasted for millions of years, and during that time they continued to evolve new forms. Some became giants that could rival modern whales in size, though those would appear later in the Jurassic. The Triassic species were the innovators, setting the blueprint. Their evolutionary success would inspire convergence again and again in later epochs. Each time life returned to the sea, whether in whales, seals, or even penguins, the same solutions appeared. Streamlined bodies, paddle-like limbs, tail propulsion. Nature, it seems, has a preferred way to design speed in water, and the ichthyosaurs were its first masterpiece. Their fossilized remains are found across every continent, even in regions that are now dry desert or mountain. The bones that once sliced through tropical waters now lie encased in stone high above sea level, a reminder of how much the planet has changed. Paleontologists studying these fossils often describe the sense of movement that seems frozen within them, The curve of the spine, the positioning of the flippers, even the texture of the surrounding rock, all suggest a creature caught mid-swim. It's as if the ocean itself decided to preserve its best swimmers as permanent memories. Beyond anatomy, ichthyosaurs tell us something about resilience. Their rise came in the wake of extinction, their success born from the emptiness left behind. They demonstrate how life not only recovers from catastrophe, but uses it as a catalyst for creativity. When the Permian seas died, the ocean was stripped of its dominant predators. Into that void came the ichthyosaurs, perfectly timed, perfectly adapted. They did not just fill a gap, they reinvented what it meant to rule the ocean. In the ecosystems they shaped, other creatures adapted in response. Ammonites developed harder shells and more complex shapes, their patterns perhaps a defense against crushing bites. Fish became faster, more agile. Even the small invertebrates that clung to reefs evolved new strategies for survival. The presence of ichthyosaurs forced everything else to keep up. They were the engines of evolutionary pressure, turning the Triassic seas into arenas of constant adaptation. Yet their world was not static. The Triassic Ocean, though abundant, remained volatile. Periodic anoxic events could devastate regions, driving species to extinction. Fluctuating climates shifted currents, forcing migrations. Through it all, the ichthyosaurs persisted. They had learned to thrive in uncertainty, to treat instability as normal. In a sense, they were the embodiment of the Triassic spirit, flexible, innovative, and endlessly mobile. If we could follow one of them now, gliding silently through that green-gold water, we might see a pattern emerge. The creature dives, chasing a school of fish. The water thickens into darkness. Its large eyes catch faint glimmers from the scales ahead. With a flick of its tail, it accelerates, closing the gap. The jaws open, snap shut in a blur. Tiny bubbles rise from the impact, catching the sunlight as they drift upward. The predator slows, the water stills, and then it turns toward the surface again. Breaking through, it exhales in a soft plume of mist before sinking back down. Everything about that moment, breath, motion, stillness, is part of the same seamless rhythm. To live in the world of the ichthyosaurs was to exist in constant motion. Rest came not from stillness, but from the flow itself. They were creatures built for a planet that was still rebuilding, yet they carried a sense of balance that the rest of the Earth had yet to find. The seas that had once been empty now pulsed with life, and at the centre of it all swam the serpents of speed, born of land, reborn in water, and perfected by the endless patience of evolution. Somewhere far below them, the depths remained silent and oxygen poor, reminders of the world that had nearly died. Above them, storms brewed across the face of Pangaea, stirring the air with heat and ash. But in between those extremes, in the blue heart of the ocean, the ichthyosaurs thrived. They were the proof that life could recover, could evolve beyond its past, could become something entirely new. Their legacy would stretch far beyond the Triassic. Long after their own lineage faded, the blueprint they embodied would endure, re-emerging in new forms whenever life returned to the water. They were not just creatures of their time, they were a glimpse of life's future. The sea had given them shape, speed, and strength, and in return, they gave it motion and memory. The Triassic oceans had found their kings, but the story was not finished. Along the coasts and in the shallows, other reptiles were following their own evolutionary paths, experimenting with different ways to hunt and survive. They were slower, stranger, and less perfect in form, but they too would claim their share of the seas. And as the ichthyosaurs ruled the open waters, these other hunters began to stir in the light of the shallows, waiting for their time to emerge. Beneath the same Triassic sun that warmed the open oceans where the ichthyosaurs glided, another realm of life unfolded in quieter, more secretive waters. Along the edges of continents and islands, in lagoons and tidal flats, the shallows formed a different kind of world, a world of ambush, camouflage, and patience. Here the water was warmer, clouded with sediment and alive with small creatures. The surface rippled gently over coral growths and beds of shellfish, and among these shifting habitats moved the hunters of the coast, the nothosaurs. They were smaller than the ichthyosaurs that ruled the deep, but no less remarkable. If the open ocean was a theatre of speed and pursuit, the shallows were a stage for stealth. The nothosaurs were built for it, with long necks, slender bodies, and limbs that blurred the line between land and sea. They were reptiles that had made a compromise with the water, comfortable enough to swim for hours, yet still capable of dragging themselves onto sandbanks or rocky shores when they needed rest. Their world was one of constant transition, a frontier where air and water merged. Imagine one resting in the shallows, its narrow head just above the surface. The eyes, large and forward-facing, scan for movement beneath the waves. A flicker catches its attention. A school of small fish, unaware of the predator watching from above. The nothosaur tenses, then slides silently forward, neck extending with mechanical precision. The jaws snap shut, breaking the surface for an instant before the creature retreats back into the green haze. A few ripples mark the end of the hunt. The water closes over them, and silence returns. Nothosaurs were not built for brute force. Their power came from flexibility and timing. Their necks contained more vertebrae than most reptiles, allowing them to strike from surprising angles. Their bodies, long and slightly flattened, could twist quickly in the water. The limbs, though not yet fully transformed into flippers, had broad paddles that gave them control. They could pivot with ease, gliding between rocks or vegetation. Evolution had sculpted them for the calm, cluttered world of coastal lagoons rather than the endless open sea. They were among the earliest marine reptiles to fully adapt to life in salt water, appearing around 240 million years ago. Fossil remains found in Europe and Asia show that they flourished in the Tethys region, where shallow continental shelves stretched for hundreds of kilometres. These were warm, nutrient-rich environments, perfect for supporting fish, crustaceans and ammonites, the nothosaurs' main prey. It's likely that they hunted by ambush, using their long necks to strike suddenly, while keeping the rest of the body still. The shape of their jaws suggests a grip designed to hold slippery prey rather than tear it apart, indicating that they swallowed their catches whole. The nothosaurs were also adaptable in behaviour. Some species may have spent time on land to lay eggs, like modern seals or sea turtles, while others might have been fully aquatic. Their anatomy suggests both possibilities. Their limb joints could support some weight, but the bones were dense enough to aid stability in the water. The fossil record even shows variation within the group, some with shorter necks and broader bodies for manoeuvring through stronger currents, others more elongated for still shallow bays. The Triassic coastlines were diverse, and so were their hunters. Their presence marked an important evolutionary stage. They were the prototype for what would come later, the plesiosaurs, the elegant predators of the Jurassic and Cretaceous seas. The plesiosaurs inherited the nothosaurs' long necks and refined them into near perfection, turning the strategy of stealth into an art form. But in the Triassic, that transition was only beginning. The nothosaurs represented the first successful model of the long-necked marine hunter, and they occupied a niche that no other creature had yet mastered. The world they lived in was complex and crowded. The coastal zones of the Tethys Sea were alive with activity. Crabs scuttled over the sand. Early coral colonies clung to volcanic rock. Ammonites drifted in the mid-water, their tentacles trailing behind their coiled shells. Small fish gathered in schools near the surface, darting away at every shadow. Above, the air shimmered with heat rising off the land. The sound of waves broke against cliffs and mangroves, mingling with the distant calls of land reptiles and early insects. It was a mosaic of life, each layer feeding the next, and within it the nothosaurs were both predators and prey. Larger ichthyosaurs sometimes ventured close to shore, and when they did, a careless nothosaur could become a meal. To avoid them, the nothosaurs stayed near cover, hugging the seabed or hiding among rocks. Their colouring likely helped them blend in, pale bellies for camouflage against the light from above, darker backs to match the seabed. This counter-shading, found in many modern marine animals, probably originated in creatures like these. Evolution, once it found an advantage, rarely let go of it. The fossils that preserve them tell much about their lifestyle. Their ribs are thick and slightly curved, giving them buoyancy control for shallow diving. Their skulls are narrow, with nostrils placed high on the snout, an adaptation for breathing while keeping most of the body submerged. Some fossils even contain remnants of small fish inside their stomachs, direct evidence of their diet. Others show healed bite marks, scars from encounters with larger predators. These bones are quiet witnesses to lives spent in constant vigilance. Over time, the nothosaurs diversified. Some species remained small, only a metre or two in length, while others grew to nearly 5 metres, formidable enough to challenge most other creatures in their environment. Their success across such a wide range of habitats shows how flexible they were. They could tolerate changes in salinity, temperature and food availability, traits that would later define the broader lineage of plesiosaurs. Evolution was experimenting, and the results were working. As millions of years passed, some descendants of nothosaurs began to change more dramatically. Their limbs flattened further, their necks became stiffer for better control, and their bodies shortened to reduce drag. These changes were the first steps toward the plesiosaur body plan, a compact muscular torso paired with long, flexible necks and flippers built purely for swimming. It's difficult to pinpoint exactly when this transformation occurred, but by the late Triassic, fossils show intermediate forms that bridge the gap between nothosaurs and true plesiosaurs. The ocean was about to welcome another master of motion. Where the nothosaurs had been stealthy ambushers, the plesiosaurs would become pursuit predators. Their 4 strong flippers, arranged in pairs, allowed them to fly through water with remarkable control. This mode of swimming, unlike the side-to-side motion of ichthyosaurs, relied on vertical strokes, something entirely new in reptilian evolution. It gave them both power and agility, letting them hover, turn or accelerate smoothly. The earliest plesiosaurs were smaller than their later Jurassic descendants, but they already displayed this revolutionary form of movement. To imagine them is to see grace expressed in another language. A plesiosaur moves through the water like a creature suspended between air and sea, its flippers undulating in slow rhythm, propelling it forward without a single wasted motion. Its long neck curves slightly, head tilting as it scans for prey. When it strikes, the movement is sudden but controlled, the jaws snapping around a fish or ammonite before returning to stillness. It is both predator and ghost, a creature so perfectly adapted to its medium that it seems part of it. Their world was richer now than when the first nothosaurs swam. The Middle Triassic oceans had fully recovered from the mass extinction that began the era. Reefs had expanded, fish populations had diversified, and the oxygen levels in the water had stabilized. There were dangers, of course, storms of volcanic activity and larger predators, but the ecosystems were balanced enough to sustain complexity. The plesiosaurs thrived in this equilibrium, spreading across the seas wherever shallow hunting grounds could be found. While the ichthyosaurs ruled the open ocean with speed, the plesiosaurs and nothosaurs dominated the margins. Their coexistence shows how evolution divides resources. Each lineage claimed its own territory and strategy, minimizing competition. In the shallows, flexibility and precision mattered more than raw speed. Every rock, every coral cluster could hide prey or danger. These were places of constant change, shaped by tides and storms, and the creatures that lived there had to be adaptable. Some plesiosaurs grew necks so long that their balance in water became a question of physics. Fossils of early genera like Pistosaurus and later forms show vertebral columns with over 40 or 50 neck vertebrae, allowing extreme reach. How they used these necks remains a topic of debate among scientists. Some believe they swept them side to side to catch schools of fish. others that they lurked motionless, extending only the head to strike unsuspecting prey. Either way, the adaptation worked. These animals prospered for tens of millions of years, far beyond the Triassic. To live in their world was to navigate an ever-changing landscape. Coastal currents shifted daily with the tides. Volcanic islands erupted, adding new land only to have it eroded again by the sea. Coral and sponge reefs grew slowly over centuries, creating mazes of structure. The water temperature could rise dramatically in shallow lagoons, forcing migrations or adaptations. The nothosaurs and plesiosaurs learned to read these cues. They followed the warmth, the fish, and the safety of familiar currents. Evolution had given them not just bodies built for water, but instincts tuned to its rhythms. Even reproduction reflected this connection. Some evidence suggests that certain marine reptiles may have begun to give birth in water during this time, an adaptation that freed them entirely from the land. If plesiosaurs followed this path, they could have lived their entire lives without ever seeing the shore. The ocean became both cradle and grave, a self-contained world that required no return to solid ground. The fossils that preserve these creatures today often appear in ancient limestone beds that once formed seabeds or coastal shelves. In places like China's Yunnan province, Switzerland's Monte San Giorgio, and the mountains of Italy, entire assemblages of Triassic marine life lie locked in stone. Fish, ammonites, and reptiles preserved together in a final tableau. Each layer represents a vanished world, each skeleton a note in the long song of life's return. When scientists uncover a nothosaur with its neck curved in a gentle arc, or a plesiosaur with its flippers outstretched, they're witnessing a frozen instant of motion, a glimpse of how life once flowed. There is something profoundly symmetrical about these creatures' existence. They began as land reptiles drawn toward the water by hunger or curiosity, and they ended as beings inseparable from it. The nothosaurs paved the way, half of their lives spent in two worlds, while the plesiosaurs completed the transformation, surrendering fully to the sea. Together, they show how evolution builds bridges across environments, not with sudden leaps, but through patient, continuous adaptation. In the quiet shallows of the Triassic, these creatures would have been a common sight. To a distant observer standing on one of Pangaea's rocky shores, the water might seem calm at first. Then, a ripple. A long, narrow head breaks the surface, eyes scanning the waves. Another shape follows, gliding beneath the waterline, its flippers moving in unison. The light catches its back, and for a moment it gleams like polished stone before disappearing again. What seems like stillness is, in truth, constant motion, the hidden pulse of an ocean alive with predators, each one shaped by millions of years of practice. As time moved forward, these coastal hunters would give rise to new lineages, refining their designs as the planet changed around them. The Triassic seas were entering a golden phase of diversity. The ichthyosaurs still reigned over the deep, but the nothosaurs and early plesiosaurs had claimed the shallows as their domain. Between them, they had turned the ocean into a mosaic of specialists, each thriving in its own niche. And while they hunted, bred and swam beneath the glow of that relentless Triassic sun, the world itself continued to shift. New predators were emerging in the deeper basins, stranger still than anything before. The age of experimentation in the sea was far from over, and soon another shape would appear in those waters, a creature that defied proportion and logic, as though evolution itself had decided to test the limits of possibility. Among all the strange forms that drifted, swam, or hunted through the Triassic seas, there was one that seemed to exist in defiance of reason. It was neither the fastest nor the largest, not the fiercest or most efficient, but it was unforgettable, a creature that looked as though nature had made a joke and then, against all odds, allowed the joke to live. Tanis Strophius. Its name means long-twisted one, and it could not have been more fitting. Nothing else from its time or any time since has looked quite like it. Imagine a reptile whose neck was longer than the rest of its body combined. Not long in proportion, but absurdly so. Nearly 3 meters of vertebrae stretching out like a living fishing rod, ending in a small triangular head. The entire animal measured about 5 to 6 meters from snout to tail, yet most of that length was neck. Its body was compact and solid, its limbs short and paddle-like, and its tail narrow. The effect was strange and unbalanced, as if someone had taken 2 different creatures and joined them by accident. And yet, the fossils tell us this design worked. Tanistropheus lived for millions of years, spreading across the ancient Tethys coastlines and leaving its imprint in stone from modern Europe to China. The first fossils of this bizarre reptile were discovered in the 19th century, but for decades scientists struggled to understand what they were looking at. At first, the neck bones were thought to belong to a flying reptile, perhaps a pterosaur. Later, some believed it might be part of a giant snake. It wasn't until more complete skeletons were found that the full picture emerged. A creature built around a single evolutionary gamble, a neck so long that it seemed to break the rules of physics. How it lived has been debated ever since. Its anatomy doesn't fit neatly into any category. Some features suggest it was aquatic, others point to life on land. Its limbs are short but strong, with flattened bones that could serve as paddles for swimming, yet they also show the structure needed to support weight. Its ribs are dense, a trait seen in many semi-aquatic animals that use their body mass to stabilize buoyancy. But the real mystery lies in the neck, how it functioned, what purpose it served, and how the animal carried it without collapsing under its own design. The neck of Tanistropheus contained only 13 vertebrae, remarkably few for such length. Each vertebra was enormously elongated, up to 20 centimeters long, forming a rigid structure with limited flexibility. This means that the creature couldn't twist or coil its neck like a snake. Instead, it likely held it straight, using small vertical and horizontal movements to adjust its aim. The bones were hollow in places but reinforced, suggesting strength without excessive weight. Even so, the physics of such a structure seem precarious. A neck of that length would create enormous leverage, making balance difficult both on land and in water. To solve this puzzle, scientists have turned to biomechanics. Models of the skeleton suggest that Tanistropheus probably lived a life of stillness, punctuated by bursts of motion. It couldn't have been a fast swimmer or an active chaser. Its body wasn't built for either. Instead, it may have been an ambush predator, lying in wait near the water's edge or hidden among submerged vegetation, extending its neck into schools of fish or crustaceans that pass too close. The jaws, filled with pointed, interlocking teeth, were ideal for catching slippery prey. A quick flick of the head, a snap of the mouth, and the meal would be caught before the victim even saw what struck it. If this image is correct, then Tanistropheus was less a hunter and more a trap. Its long neck allowed it to strike without moving the rest of its body, avoiding the ripples and vibrations that might alert prey. It could remain still for long periods, conserving energy, its head suspended above the water like a motionless periscope. When the time came, it could strike with speed, the neck snapping downward like a spring released. Such a strategy required precision rather than power, patience rather than endurance. In the unstable world of the Triassic, where conditions changed constantly, this patience might have been its greatest strength. The fossils show that there were at least 2 distinct species of Tanistropheus, one large, one smaller. This discovery suggests that the genus occupied multiple ecological niches. The larger form, reaching up to 6 meters in length, likely hunted in coastal waters and lagoons, preying on sizable fish and squid. The smaller species, around 2 meters long, may have lived closer to the shoreline, feeding on smaller aquatic prey and insects. The coexistence of both forms in the same regions points to an ecosystem rich enough to support multiple variations of the same bizarre design. Evolution had taken a single strange idea and multiplied it, refining it for different roles. If we could stand on the shore of the Tethys Sea and see one, it might look both alien and strangely graceful. Its body would rest just below the surface, legs paddling gently to maintain position. The neck would rise slightly, the head poised, motionless but alert. The water would ripple around the thin outline of its body, and for long minutes nothing would happen. Then, in a blur too fast for the eye to follow, the neck would dart forward, the jaws breaking the surface with a splash, and the creature would swallow its catch whole. For a moment the water would shimmer with disturbed light, then settle again as if nothing had happened. Some reconstructions depict Tanystropheus as primarily aquatic, its neck trailing behind it as it swam, but this seems unlikely. The structure of its neck vertebrae suggests limited movement and significant drag underwater. More likely, it stayed near the surface, floating and striking downward or outward. Others propose it hunted from land, standing on the shore and dipping its head into the water like a heron. This idea fits its anatomy well. The limbs could have supported it on solid ground, and the neck was long enough to reach into the shallows. It might have stood motionless for hours, its body hidden among rocks or vegetation, while its head explored the water like an extension of its senses. Whichever lifestyle it followed, one thing is clear: Tanystropheus was a creature that made the impossible work. It defied the usual patterns of evolution, creating a form so extreme that it shouldn't have been viable, and yet it was. It survived for millions of years across vast stretches of coastline, proving that even the strangest ideas can succeed if the environment allows them. Nature, after all, doesn't care about elegance or logic. It only cares about results. Its existence tells us something profound about the Triassic world. This was a time of experimentation, when ecosystems were still finding balance. The extinction that ended the Permian had cleared away most established species, leaving open niches everywhere. In that vacuum, evolution tested new possibilities. The Triassic seas became a workshop of forms: streamlined ichthyosaurs, armoured placodonts, serpentine nothosaurs, and now this improbable creature with a neck longer than sense should permit. Each was a response to opportunity, a different answer to the same question: how to live in water. The presence of Tanystropheus also reveals how diverse the Triassic coasts were. Its fossils appear in what were once subtropical environments, regions of lagoons, deltas, and tidal channels. These were places of calm water and rich life, where fish gathered in abundance and plants rooted in soft sediment. For an ambush predator, it was paradise. It didn't need to chase its prey. The prey came to it. Its long reach let it strike from concealment, avoiding detection until the final moment. Its heavy body kept it stable as it lunged, and its teeth ensured nothing escaped once caught. Every part of its anatomy, however strange, had a purpose. Its neck, though rigid, was supported by strong tendons and ligaments that anchored deep into the torso. The muscles along the back and shoulders were thick, providing both power and balance. When the head darted forward, the body likely shifted slightly in counterbalance, the tail and limbs adjusting to keep it steady. It was a delicate interplay of mechanics, every movement coordinated to prevent collapse. In life, it must have looked both ungainly and precise, an animal that seemed to defy gravity but never lost control. Modern analogues are rare, but some comparisons can be made. Herons and anhingas on land use similar strategies, waiting motionless before striking with lightning speed. Certain turtles and snakes employ long necks to reach prey while keeping their bodies hidden. Tanystropheus may have been a reptilian equivalent of these forms, adapted not to speed or power but to geometry. It extended its reach into new ecological territory without moving its bulk. The ocean rewarded this strategy because it minimized risk and energy use. In evolutionary terms, it was elegant, even if its appearance was not. Its discovery has provided scientists with one of the best examples of how deceptive first impressions can be in paleontology. When early paleontologists reconstructed it, they often placed the neck too high or too flexible, imagining a serpent-like animal that could coil or lift its head high like a giraffe. Later, more careful analysis showed that it couldn't have moved that way at all. Its neck was stiff, its head movements limited to a narrow range. What looked ungainly in sketches proved, in reality, to be a masterclass in evolutionary economy. The creature didn't need to move much. It only needed to move once, at the right moment. Its predators, however, would have tested that patience. Larger ichthyosaurs and marine crocodile-like reptiles roamed the same coasts. To survive, Tanistropheus likely relied on stealth and camouflage. Its body might have been patterned in muted greens and browns, blending with the reflections of the water and the vegetation along the shore. When danger approached, it could retreat into deeper water or flatten itself against the bottom. Its body shape made it difficult to grab, and its long neck allowed it to keep its head and senses alert even while the rest of it stayed hidden. Fossil evidence suggests that these animals lived in groups, or at least shared habitats in large numbers. Sites in Switzerland and the Middle East contain multiple specimens found together, perhaps the remains of individuals drawn to the same feeding grounds. Whether they interacted socially is unknown, but the possibility adds another layer of fascination to their story. It's easy to imagine a cluster of them, partially submerged along a Triassic lagoon, each waiting silently, their long necks angled toward the same patch of water, a scene so still that it might go unnoticed until one suddenly moved, sending ripples across the calm surface. Their extinction, like their lives, remains partly mysterious. They disappeared near the end of the Triassic as climates shifted and sea levels changed. The shallows that had supported them may have dried or become too unstable. New predators appeared, competition increased, and the delicate balance that had allowed their design to work began to fail. But in the fossil record, they left behind something more lasting than bones. They left a reminder that evolution is not a straight path toward efficiency. It's a vast field of trial and error, where even the most unlikely creations can thrive if they fit the moment. In that sense, Tanistropheus was not a mistake. It was a message. It proved that life could bend the rules of design, stretch the limits of anatomy and still succeed. Its long neck, its awkward body, its improbable proportions, all of them were simply the outcome of adaptation finding a new route. When the Triassic world asked what else was possible, this creature answered. In the calm waters of that ancient sea, it must have looked like something out of place, yet utterly at home. The sun shimmered on its back. The water rippled softly around its sides. Its head hovered above the surface, waiting for the next flicker of movement beneath. Around it, the ocean hummed with life, fish darting through shadows, ammonites drifting like tiny planets, the occasional shadow of an ichthyosaur passing in the distance. And amid it all, this improbable shape held its ground, surviving by balance, patience, and precision. The Triassic period was full of predators that made sense. Streamlined hunters built for pursuit, armoured grazers built for defence. But Tanistropheus was neither. It was something in between, a creature that shouldn't have worked but did. A quiet testament to the creativity of evolution when freed from constraint. It existed because the world allowed it, because the oceans of that time were generous enough to make room for even the strangest of dreams. And as those long necks dipped once more beneath the shimmering surface of the Tethys, the seas that had birthed so many new forms were already preparing for their next experiment. The age of the odd was far from over, and the predators that followed would push the boundaries even further, shaping the Triassic oceans into a realm where power, speed, and strangeness all found a place to thrive. By the middle of the Triassic, the seas had grown crowded. Life had not only recovered but overflowed, filling every space that light and oxygen could reach. What had begun as fragile experimentation after the Great Extinction had now become an ecosystem of full confidence. The ocean was no longer a place of chance but of mastery. The small fish darted through reefs, the ammonites drifted like coiled lanterns through the green light, and the marine reptiles, once tentative newcomers, had claimed their realms. But with abundance came competition, and competition bred predators that redefined what it meant to rule the sea. The balance that had held for millions of years began to shift. The ichthyosaurs, the swift lords of the open ocean, and the nothosaurs and plesiosaurs, the subtle hunters of the shallows, no longer hunted unchallenged. New forms were evolving, reptiles with stronger jaws, heavier bodies, and minds tuned entirely for domination. The Triassic had entered an age of escalation, when every adaptation invited another in response. It was a time when the boundaries between predator and prey hardened, and when power became the defining language of survival. Among the earliest to emerge were the thalatosaurs, long-bodied reptiles that seemed to have occupied an evolutionary middle ground between the agile swimmers and the powerful predators that would come later. Their name means sea lizard, and it suited them well. They were long, flexible and serpentine, with limbs adapted into flippers and tails built for propulsion. Unlike ichthyosaurs, they lacked the sleek perfection of form, but they compensated with agility and sharpness. Their narrow jaws were lined with small teeth suited for grasping fish and soft-bodied animals. They lived in the coastal zones of the Tethys, where their speed and maneuverability allowed them to weave through rocks and reefs with precision. In them, we see the first signs of the new order taking shape. They were opportunistic, quick to exploit every opening. The fossil record shows that some thalatosaurs developed variations in their teeth, some sharp and pointed for catching fish, others rounded and crushing for breaking shells. They were diversifying rapidly, adjusting to the shifting tapestry of life around them. But their reign was brief. They were the bridge between worlds, not the rulers of them. Soon, heavier, more formidable predators would arrive to claim their place. The next wave came from a different lineage altogether. Reptiles that had once walked the land but found power in water. These were the ancestors of the great marine predators that would one day dominate the Mesozoic oceans. Creatures like the mosasaurs that would follow in distant ages. But in the Triassic, their prototypes were smaller, leaner, and just as deadly. They were crocodiliforms, early relatives of the crocodiles that still inhabit our planet today. These early crocodile-like reptiles, often called thalatosaucians, were not yet the amphibious lurkers we associate with modern crocodiles. They were more active swimmers, streamlined and muscular, with limbs that had begun to flatten into flippers. They hunted in both rivers and coastal seas, using their powerful tails to burst forward in short, explosive strikes. Their jaws were long and narrow, filled with conical teeth that left no doubt about their purpose. Where the nothosaurs and placodonts had hunted by stealth, these newcomers hunted by force. They could seize large prey, thrash it into submission, and tear it apart. It was the beginning of a new era, one where violence became a strategy refined to art. The oceans reflected this transformation. The prey species grew faster, leaner, and more wary. The ammonites developed stronger shells with intricate chambers to resist pressure and damage. Fish evolved better vision and tighter schooling behaviour. Even the smaller marine reptiles became more cautious, adapting to hide among reefs or in murky waters. Each new predator pushed evolution forward, and the pace quickened. In less than 10 million years, the hierarchy of the ocean had rearranged itself. The apex predators that finally emerged from this evolutionary race were remarkable not only for their power, but for their specialization. They weren't merely bigger, they were smarter in their design, more efficient in their use of energy, more versatile in the range of prey they could dominate. The ichthyosaurs themselves evolved new, larger forms. Species like Symbospondylus reached lengths of more than 10 meters, with skulls stretching nearly 1.5 meters. They were the leviathans of their time, built for deep diving and long pursuit. Their eyes, large even by ichthyosaur standards, suggested hunting in twilight depths, where they could surprise prey from below. Their jaws could crush large fish and smaller marine reptiles with ease, Cymbospondylus was not a sleek dolphin-like swimmer, but something more imposing. Its body was long and muscular, its head massive compared to its torso, and its teeth thick and robust. It wasn't built for bursts of speed, but for relentless endurance, gliding through the open ocean with patient dominance. It could follow migrating schools of prey for days, diving deep and resurfacing in rhythm with the pulse of the sea. In many ways, it was the first true apex predator of the open Triassic Ocean, one that feared little and fed on nearly anything. While Cymbospondylus ruled the deep, other giants rose closer to shore. Nothosaurs evolved into more specialized forms, culminating in the pliosaurs and early plesiosaurs that would later dominate the Jurassic. But even in the Triassic, their ancestors had begun to experiment with the anatomy of power. Shorter necks, broader skulls, and stronger flippers appeared in some species, traits that favoured rapid acceleration and deadly bites over stealth. These transitional forms represented a shift in strategy, from patience to pursuit. The ocean was no longer a place to hide, it had become a battlefield. The evidence of this arms race lies in the fossils themselves. Skulls from the late Triassic show bite marks that match the jaws of other marine reptiles. Predators were attacking not just prey, but each other. It was an age of constant testing, where every advantage was temporary and every weakness exploited. For millions of years, the oceans teemed with combatants locked in silent struggle, their bones recording the scars of a world learning the mechanics of dominance. Even the environment conspired to shape these predators. The Triassic seas were warm and shallow, ideal for supporting high metabolic activity. The high levels of carbon dioxide in the atmosphere meant the oceans held vast amounts of dissolved nutrients, fueling plankton blooms that sustained entire food webs. This abundance of energy at the bottom of the chain allowed greater size and power at the top. The apex predators thrived because the seas beneath them could afford to feed them. To imagine these creatures moving through that world is to picture precision, wrapped in raw force. An ichthyosaur gliding through a school of fish, its jaws snapping like steel traps. A thalattosaur twisting between coral spires, teeth flashing in the filtered light. A proto-crocodilian lunging from a rocky ledge, its momentum shattering the surface in a burst of spray. Each encounter left ripples across the sea, echoes of a time when the oceans were ruled by teeth and instinct. The rise of these predators didn't happen in isolation. It was part of a broader pattern that stretched across the planet. On land, the first dinosaurs were beginning to appear, small and quick, but destined for greatness. In the air, the earliest pterosaurs had taken flight, claiming the skies just as marine reptiles claimed the seas. The Earth was reorganizing itself into new hierarchies. In every environment, the dominant forms were no longer the sluggish or the heavily armoured, but the fast, the efficient, and the relentless. The Triassic had become the age of active predators. The success of these marine hunters also influenced the behaviour of the prey they pursued. Ammonites developed more complex shell structures, their internal chambers becoming labyrinths that absorbed shock and pressure. Fish grew larger, some adopting schooling patterns that confused attackers. Even plankton evolved faster reproductive cycles to keep up with the rate of consumption. The result was an ecosystem that seemed alive in every direction, a constant flow of adaptation and response. The Triassic seas were no longer recovering from disaster. They were in full bloom, a living demonstration of life's ability to turn chaos into order. In this order, the apex predators played a paradoxical role. By keeping populations in check, they prevented overgrowth and collapse. Their presence ensured balance even as they embodied destruction. When they hunted, they selected the weak, the slow and the sick, strengthening the species that survived. It's a truth that persists in every ecosystem, from the Triassic seas to modern oceans. Power, used relentlessly, becomes a force of equilibrium. As the Triassic drew toward its later stages, the variety of marine reptiles reached its zenith. There were creatures for every depth, every niche. Some species hunted in the daylight shallows, others in the blackness below. Some specialized in hard-shelled prey, others in fast-moving schools. The diversity was astonishing, a web of life so intricate that even minor changes in temperature or salinity could ripple across entire ecosystems. Yet, for all this complexity, the apex predators sat at the top with calm certainty. They had no rivals but each other. It's easy to think of them as mindless killers, but their survival depended on more than aggression. They needed endurance, intelligence, and timing. The ocean favoured those who could read its patterns, the shifts in current, the migrations of prey, the approach of storms. A successful predator was not just strong, but adaptable, able to adjust to new conditions quickly. Fossil evidence suggests that some ichthyosaurs and other large marine reptiles undertook long migrations, possibly following breeding or feeding grounds across entire ocean basins. Their bones record growth rings like those of trees, each layer marking the rhythm of a life lived to the tempo of the sea. In those bones lies the story of the ocean's transformation. The Triassic began as a world of survival, its waters empty and lifeless. By its middle, it had become a realm of abundance and conflict. By its end, it was an empire of predators, ruled by creatures that had mastered every dimension of their environment. They swam not just to feed, but because motion itself was life. The ocean had no walls, no boundaries, only movement, and they were built to inhabit it completely. The rise of the apex predators was the natural consequence of recovery. When life fills a vacuum, it doesn't stop at sufficiency. It overshoots, it competes, it escalates. In the Triassic seas, that escalation produced some of the most formidable animals the planet had ever seen. And though their time would pass, replaced by new dynasties in the Jurassic and beyond, their influence would linger. Every great predator that came after, every shark, whale, and marine reptile, carried echoes of the design perfected here. The Triassic Ocean, once silent after the world's greatest extinction, now thundered with motion. The surface rippled with life, and below it, shadows moved with purpose and hunger. The balance that had once depended on survival alone now depended on dominance. The apex predators had risen, and the sea itself had learned the rhythm of pursuit. Far beneath the surface, where light faded into blue and then into black, their shapes passed through the darkness like dreams, silent, efficient, eternal. They were the culmination of everything the Triassic had been building toward. Resilience turned to strength, experimentation turned to mastery. And as they glided through those depths, the ocean that had birthed them continued to evolve, carrying their legacy forward into the next chapter of life beneath the waves. Beneath the gleaming surface of the Triassic seas, below the shimmer of sunlight and the restless dance of waves, there was another world. A world few creatures from the air or land would ever see, yet one that thrived with quiet persistence. It was darker here, cooler, and filled with a hum that never stopped. The steady vibration of life rebuilding itself from the chaos of extinction. The predators that ruled above were only part of the story. The true foundation of these oceans lay below them, in the layers of depth where light surrendered to shadow and colour dissolved into shades of blue and green. Near the surface, sunlight still reached through the water, fragmented by motion. Every particle suspended in it caught and scattered the rays, turning the upper layers into liquid gold. This zone, shallow but vital, was where energy from the sun became life. Here, plankton multiplied endlessly, forming vast invisible blooms that drifted with the currents. They were small beyond imagination, but together they shaped the chemistry of the ocean, feeding everything from the smallest fish to the largest reptiles. Each breath of an ichthyosaur, each movement of a plesiosaur's flipper, depended on this microscopic community floating in the light. As one descended deeper, the brightness began to fade. The greens dimmed to teal, then to grey-blue, and soon there was only a faint glow filtering down. In this twilight region, Fish with larger eyes cruised slowly through the dimness, their scales catching the last fragments of light. Ammonites pulsed through the water like drifting lanterns, their tentacles curling and uncurling as they propelled themselves forward. Their coiled shells glistened faintly with pearlescent sheen, each chamber filled with gas to maintain buoyancy. Schools of small fish moved in unison through this zone, turning together as if guided by a single thought. Predators from above sometimes descended here, their shadows slipping silently through the fading light before vanishing into deeper blue. The seafloor below was not barren but rich with texture. Fields of sponges grew in thick mats, filtering water through intricate networks of pores. Crinoids, ancient relatives of sea stars, waved delicate arms toward the current, catching drifting particles. Shellfish clung to rocks, and early coral-like organisms built frameworks of calcium that would, over time, form reefs. These reefs were different from modern coral structures, simpler in form but no less alive. They provided shelter for countless creatures, crustaceans hiding in crevices, small fish weaving between outcrops, and soft-bodied animals anchored to the substrate. Every rock, every mound of sediment was occupied. Moving slowly along the bottom were the grazers and scavengers that formed the silent workforce of the ocean. Placodonts, with their heavy shells and crushing teeth, prowled among the coral beds, feeding on mollusks and urchins. Their movements stirred up clouds of silt that drifted upward in slow spirals, briefly obscuring the view before settling again. Nearby, sea urchins crept across the sand, scraping surfaces clean of algae. Tiny shrimp picked at detritus, recycling nutrients into the endless loop of life. The Triassic sea floor was a mosaic of motion, each organism contributing to the quiet machinery that kept the ocean alive. Occasionally the calm would break. A shadow passed overhead, a predator diving from the shallows or the open ocean beyond. Its shape would glide silently through the gloom, the smaller creatures scattering into holes and crevices. In moments like this, the interconnectedness of the ecosystem revealed itself. Every flick of a tail, every heartbeat of a swimmer, sent ripples through the food chain, signalling both danger and opportunity. The deep world below the surface was not isolated. It was tied to everything above it, bound together by the shared flow of water and life. The chemistry of these depths was complex and unstable. The Triassic oceans were still recovering from the toxic legacy of the mass extinction that had preceded them. Pockets of oxygen-poor water still existed, especially in deeper basins where circulation was weak. These anoxic zones formed invisible boundaries. Above them life flourished, below it dwindled. Yet even in the margins of these lifeless regions, certain bacteria thrived, feeding on sulfur and minerals that seeped from the Earth's crust. They formed mats on the seafloor, glowing faintly in chemical reactions unseen by the human eye. From these microorganisms came the first whispers of future ecosystems, proof that even where oxygen failed, life found a way. Above these shadowy plains, schools of small predatory fish hunted through the half-light. Some had evolved bioluminescent organs, faintly glowing to lure prey or communicate. Their eyes were proportionally huge, able to detect movement in near darkness. To watch them was to see a silent ballet of light and motion, brief flashes as bodies turned, the rhythm of survival playing out without sound. It was in these mid-depth zones that many of the Triassic Ocean's dramas unfolded, unseen by the world above. The currents that flowed through these layers connected everything. They carried nutrients from the surface downward, bringing life to the depths, and returned with cold, mineral-rich water from below. These movements shaped migration patterns, drawing plankton blooms across vast distances and guiding the paths of the creatures that fed on them. The ichthyosaurs and other marine reptiles, though they spent most of their time near the surface, followed these invisible highways. They could sense the changes in temperature and chemistry, their instincts guiding them along routes that promised food and safety. Each region of the Triassic Ocean had its own character. The shallows near the coast were warm and crowded, the mid-depths calm but active, and the deeper basins cool and silent. But even in the stillness of the depths, life persisted. Fossils show that some species of fish and invertebrates adapted to these darker realms, evolving slow metabolisms and specialized feeding methods. Some fed on sinking detritus, fragments of plankton, fecal pellets, and decaying bodies drifting down from above. This rain of organic matter, known as marine snow, was the quiet heartbeat of the sea, connecting life from top to bottom. Every creature that lived and died near the surface eventually became nourishment for the world below. Even the predators contributed to this cycle. When an ichthyosaur died, its body would sink slowly into the depths, its flesh becoming a banquet for scavengers. Crustaceans, worms, and fish would converge, stripping the carcass until only bones remained. Over time, minerals replaced the organic material, turning those bones into fossils. Millions of years later, those fossils would rise again with the movement of tectonic plates lifted from the seabed to the surface, waiting to be found. Each one a record of this continuous transformation. The reefs too grew and died in rhythm with the sea. Storms would break sections apart, scattering fragments across the seabed. New growths would anchor themselves on the ruins, turning destruction into foundation. The Triassic reefs may not have glowed with the colours we associate with modern coral, but they were living cities nonetheless, dense, complex, and alive with motion. Small fish sought shelter among their spires, predators patrolled their perimeters, and scavengers cleaned their surfaces. These reefs represented stability in a world otherwise marked by upheaval. The soundscape of this undersea realm would have been soft but constant. The crackle of shifting sediment, the clicking of shells, the faint rumble of distant volcanic vents, all blending into a steady pulse. The water carried vibrations farther than air ever could, allowing creatures to sense movement long before they could see it. To live here was to listen as much as to see. Every motion had meaning, every disturbance a potential sign of life or death. The ocean's balance depended on this web of connections. When plankton thrived, fish populations rose. When fish flourished, predators grew stronger. When predators overreached, the system corrected itself. It was a living equation, sustained by constant motion. In this sense, the Triassic Sea beneath the surface was not just a habitat, it was an organism in its own right, breathing through the exchange of nutrients and energy, pulsing in rhythm with the tides and seasons. The variety of life here was astonishing. Alongside the familiar forms, fish, ammonites, sponges, were creatures that defy easy classification. Small, ribbon-like animals drifted through the current, neither true fish nor invertebrate. Tiny crustaceans floated in the plankton layers, their transparent bodies almost invisible. Early squid-like creatures propelled themselves with gentle jets of water, their tentacles reaching into the dark. Each was part of a system that balanced efficiency with diversity, ensuring that the loss of one species would not collapse the whole. Even the water itself was alive with interaction. Chemical exchanges between the atmosphere and ocean controlled the levels of oxygen and carbon dioxide, shaping both climate and biology. The Triassic world was hotter than ours, but it was stable enough to sustain life across every latitude. The absence of polar ice meant that warm currents could flow unimpeded around the planet, turning the oceans into a global network rather than isolated basins. For the creatures that lived within it, this meant opportunity. They could spread across entire continents, following the gentle pull of currents from one region to another. In the deepest reaches, where the last remnants of light faded entirely, the ocean floor was shaped by forces more ancient than life itself. Volcanic vents spewed minerals into the water, creating chemical oases that supported strange bacterial colonies. These bacteria, feeding on hydrogen sulfide instead of sunlight, formed the base of an entirely different food chain. Small worms, mollusks, and crustaceans fed on them, their translucent bodies glowing faintly from within. These hidden ecosystems were reminders that life needed neither warmth nor light, only energy and time. Everywhere one looked, the sea spoke the same language of adaptation. It was not a world of chaos but of balance found through endless variation. The predators that swam above depended on the unseen multitudes below, and those multitudes in turn relied on the constant recycling of nutrients that began with death. The surface shimmered with beauty, but the depths held the truth of how life endures, quietly, steadily, invisibly. If one could drift through those depths without fear, one might see scenes of haunting calm. The skeleton of a dead ammonite resting on the sand, its shell half buried, tiny creatures moving in and out of its hollow chambers, a school of small fish gliding through a shaft of light that somehow reaches down from far above. The slow undulation of a placodont as it grazes across the seafloor, its shell reflecting the dim glow. Each moment ordinary, yet together forming a tapestry more intricate than anything above. The Triassic Ocean beneath the surface was the unseen foundation of an entire era. Its quiet cycles sustained the power and motion that defined the reptiles above. It was the heartbeat beneath the spectacle, the calm beneath the chase. And though the creatures that swam in its depths are long gone, their pattern remains. Every ocean since has followed the same design, light above, shadow below, life in between, endlessly transforming. The story of the Triassic seas was not one of chaos, but of equilibrium earned through struggle. The world beneath the surface was its centre, the place where life remembered how to rebuild. As the eons turned and the oceans deepened, this invisible realm continued its steady work, preparing for the next stage in Earth's long, unbroken rhythm of survival. By the time the Triassic seas reached their fullest bloom, the ocean had grown crowded with giants. The creatures that had once been fragile survivors were now perfected hunters, sculpted by millions of years of adaptation. The predators that prowled these waters no longer resembled their distant ancestors on land. They were entirely of the sea, shaped by its laws and rhythms, their bodies attuned to its currents, their senses tuned to the faintest pulse of movement in the water around them. The Triassic giants had arrived, and with them came an age of power and precision unlike anything that had come before. They were not monsters in the way we imagine monsters, clumsy, oversized, or savage. Their strength was deliberate, refined by necessity. They did not rule through chaos but through mastery. Each was an instrument of survival, honed to do one thing perfectly, to hunt. And for every predator that rose, prey evolved alongside it, shaping its movements, its behavior, its instincts. The dance between hunter and hunted was the defining rhythm of these seas, and in that rhythm balance was maintained. The largest of the Triassic marine reptiles, the ichthyosaurs like Cymbospondylus and Shonosaurus, dominated the open waters. Their size alone set them apart, some stretching more than 10 meters in length, their long bodies and sweeping tails moving with a calm power that smaller creatures could never match. They were the apex hunters of the open ocean, gliding through the deep in search of fish and cephalopods. To see one would have been to witness a living vessel of motion, a creature that seemed carved from the sea itself. Their movements were slow and graceful at rest, but when they struck, the change was instantaneous. A flash of muscle, a blur of motion, and the silence of the ocean was broken for only a heartbeat before it closed again. Their prey was as diverse as their size demanded. The smaller fish that filled the shallows often moved in schools for safety, but in the open sea, safety was an illusion. The ichthyosaurs would approach from below, using the light above as camouflage. The sudden shape rising from the depths gave the prey no warning, only a shimmer in the water before the jaws opened. The teeth, conical and interlocking, were not made for cutting, but for gripping. Once caught, the prey had no chance of escape. Within seconds it disappeared, swallowed whole as the hunter continued its glide, never slowing. Among the prey that fill these seas, the ammonites stood out as both survivors and symbols of adaptation. Their shells, coiled and chambered, had evolved over generations to withstand pressure and attack. The complex sutures between their shell walls, those intricate fractal-like patterns, were not decoration but reinforcement. Each curve and fold added strength, allowing them to resist crushing jaws. Yet even these defences could not always save them. Fossilized ammonite shells are sometimes found with circular holes punched clean through, matching the bite marks of marine reptiles. Each one is a frozen story of pursuit, capture, and consumption, told in stone. Other prey adapted in different ways. Fish grew faster, leaner, their scales thinner to reduce drag. Some species developed deep bodies that allowed for quick turns, an advantage against pursuit. Others relied on schooling behaviour, creating confusion through numbers. When a predator attacked, the school split in a burst of motion, each individual trying to become invisible among the chaos. The strategy did not always work, but it increased the odds of survival enough to matter. In evolution's long arithmetic, every advantage counted, no matter how small. Not all the giants of the Triassic were hunters. Some were grazers or opportunists, living off the bounty of smaller creatures that crowded the reefs and seafloor. The plecodonts, with their thick shells and crushing teeth, were among these. They moved slowly, feeding on shellfish and crustaceans. Their flat, grinding jaws could crush even the hardest shells, turning them into fragments that settled on the seafloor as part of the endless cycle of decay and renewal. Though they lacked the speed and grace of the ichthyosaurs, they were no less successful. In a world where predation ruled, their armour and patience kept them safe. In the mid-depths, other forms of life had grown large too. Cephalopods, relatives of modern squids and octopuses, had evolved long, streamlined bodies and fins that allowed them to manoeuvre with precision. Some grew over a metre in length, their tentacles tipped with hooks or suckers lined with tiny teeth. They hunted fish and smaller mollusks, and in turn were hunted by the reptiles that ruled above. The Triassic Ocean was a web of predators and prey, each both hunter and hunted, each part of the same continuous chain. The plesiosaurs that patrolled the shallows and continental shelves brought a different kind of elegance to the hunt. Their long necks and flexible bodies allowed them to strike from unexpected angles, turning slowly and silently before lunging at prey. They often hunted near reefs and rocky outcrops where fish and ammonites gathered. With 4 flippers working in coordinated rhythm, they could hover almost motionless in the water, then surge forward in a burst of speed. Their strikes were precise and controlled, leaving little room for escape. Some scientists believe that certain plesiosaurs may have hunted cooperatively, perhaps herding schools of fish toward shallow water where escape was impossible. Whether this behaviour was instinct or intention, it shows a level of adaptability that speaks to their intelligence. The ocean favoured those who could learn, who could sense patterns in the flow of life and take advantage of them. These reptiles, though driven by instinct, moved through their world with awareness. They read the currents, the vibrations, the faint signals that told them when to strike and when to retreat. The prey were no less attuned. Many fish evolved sensory organs that could detect pressure changes in the water, allowing them to feel the approach of predators. Some developed reflective scales that confused visual hunters. Others relied on bursts of speed so intense they could outpace danger for the few seconds that mattered. In every movement, in every flick of a tail, there was calculation. The Triassic seas were not a place of mindless slaughter, but of constant, intricate interaction. Every act of predation balanced by an act of escape. The open ocean held its share of spectacle, but the coastal zones were where the most dramatic encounters unfolded. In those shallow regions where light and shadow mingled, the battles between predator and prey were close and personal. The water churned with silt and fragments of shell. Every hunt stirred the environment, and every success or failure left marks on the ecosystem. The nothosaurs, with their elongated bodies and quick necks, patrolled these borders tirelessly, seizing fish and crustaceans before slipping back into cover. Their efficiency kept the coastal food chains in constant motion, preventing stagnation. It was in this dynamic equilibrium that the giants thrived. Their success depended not only on strength, but on the balance maintained by everything smaller than themselves. Without the plankton blooms, there would be no fish. Without fish, no predators. The web of life stretched from the microscopic to the colossal, and every strand mattered. Even the death of a single giant had meaning. When one fell, its carcass fed countless others, scavengers, bacteria, and creatures that lived only on decay. The ocean consumed everything, even its rulers, and in doing so, renewed itself. There were times when the calm was shattered by forces beyond the reach of biology. Underwater earthquakes shook the seabed, dislodging sediments and changing the landscape overnight. Volcanic eruptions poured gases into the atmosphere, altering temperatures and currents. These events caused sudden disruptions in food availability, driving migrations and extinctions, but life adapted, always finding new balance. The Triassic Ocean was resilient because it was interconnected. No single failure could end it. Some of the most impressive fossils from this era capture these relationships in a single moment. In one slab of limestone from the Alps, an ichthyosaur fossil is found with the remains of an ammonite still lodged in its jaws, a frozen instant of predation interrupted by death. In another, the bones of a plesiosaur rest beside the shattered shells of its last meal. These records tell stories of motion and hunger, of creatures locked in the eternal rhythm of life and loss. They show us that the giants were not distant or abstract. They were part of a system as real and intricate as any that exists today. The Triassic seas were also home to mystery forms, animals whose exact roles are still debated. Some were slender, ribbon-bodied swimmers with delicate fins that might have fed on plankton or small crustaceans. Others were armoured, slow-moving bottom dwellers that used crushing jaws to break coral and shells. The variety of shapes and strategies reflected the ocean's generosity. In its warmth and abundance, it allowed life to experiment without fear of immediate extinction. Diversity was not a luxury but a necessity, ensuring survival through every shift of climate and current. In this world of perpetual motion, the giants did not dominate through cruelty, but through harmony with their surroundings. They were extensions of the ocean's power, embodiments of its endless cycles. When they swam, they moved with the same rhythm as the tides. When they hunted, they did so with the precision of natural law. There was no malice in their pursuit, no waste in their hunger. The prey, too, played their role with equal purpose, keeping the balance intact through their own strategies of survival. From a distance, the Triassic Sea must have appeared tranquil, just endless blue under a relentless sun. But beneath that stillness was the pulse of a living world, an unbroken current of energy flowing from the smallest organism to the largest predator. Every drop of water carried the memory of countless lives, the chemistry of ancient breaths, the fragments of shells ground to dust and reborn as new forms. The giants swam through that history, unaware of it, but inseparable from it. Their reign would not last forever. The same geological forces that had given them space and sustenance would eventually change again. The continents would continue to drift, the seas to rise and fall, and with each shift, some creatures would vanish while others took their place. But for tens of millions of years, the Triassic giants ruled without rival. They were the architects of the ocean's modern form, the pioneers of marine dominance, and the proof that life, when given time, always reaches for greatness. Even now, their shapes echo in the creatures that came after. The streamlined bodies of whales, the hunting patterns of sharks, the coordination of dolphins, all trace their lineage back to these Triassic pioneers. The relationship between predator and prey, the delicate exchange of strength and vulnerability, remains unchanged. The Triassic giants are gone, but their rhythm endures, carried forward in every tide, in every migration, in every breath of life that still depends on the sea. And as the eons turned and the Triassic world inched toward its close, the harmony of this ocean would once again be tested. The balance between life and environment, between predator and prey, would be challenged by forces greater than any creature could withstand. The sea that had given rise to the giants would soon be reshaped by catastrophe once more, and everything that had been built so patiently would face its reckoning. For millions of years, the Triassic oceans had been a story of recovery and triumph. They had grown from near emptiness into a realm of abundance and balance, a living network that stretched across the world. But nothing in Earth's history remains still. Every rise carries within it the seed of decline, every flourishing a hidden fragility. Beneath the calm surface of the late Triassic seas, the first signs of collapse began to stir. Subtle at first, invisible to the creatures that swam through them, but gathering strength all the same. The changes began, as they so often did, deep within the planet. The continents of Pangaea, long fused into a single massive landmass, were starting to tear apart. Beneath the crust, magma shifted and pressed upward, cracking the supercontinent along fault lines that would one day become the Atlantic Ocean. These rifts released vast amounts of carbon dioxide and methane into the atmosphere, gases that trapped heat and disturbed the climate. The process was slow on a human scale, but devastatingly fast in geological terms. Within a few million years, the planet's balance began to tilt. The oceans, so dependent on temperature and chemistry, were among the first to feel the consequences. Surface waters warmed, currents shifted, and deep circulation faltered. Regions that had once been rich in oxygen grew stagnant. In the shallows, algae blooms spread across vast areas, choking reefs and consuming oxygen as they decayed. In deeper basins, anoxic layers expanded, driving many species to extinction. It was a familiar pattern, the same chain reaction that had ended the Permian and would repeat again at other times in Earth's history. Warmth led to stagnation, stagnation to suffocation, and suffocation to death. For the creatures that ruled the seas, the changes were both environmental and biological. The delicate balance between predator and prey began to unravel. As oxygen declined, the smaller fish and invertebrates that formed the foundation of the food chain suffered first. Without them, the larger predators found less to hunt. Populations that had once been stable began to collapse. The ichthyosaurs, though powerful and adaptable, could not find enough food in some regions. The reefs that had sheltered the juveniles of countless species began to die, leaving bare rock behind. Storms grew stronger as the planet warmed. The difference between ocean and air temperature intensified, driving massive cyclones across the seas. Waves tore apart shallow habitats and scattered the remains of coral and shell across the seafloor. For the plesiosaurs and nothosaurs that depended on those coastal zones, the world grew unpredictable. Their prey migrated or vanished. The water's chemistry changed so rapidly that entire populations disappeared in a geological instant. The calm rhythm of life that had lasted for millions of years broke apart into chaos. The volcanic eruptions that drove this transformation were immense beyond comprehension. In what is now the central Atlantic region, enormous fissures opened, pouring out lava over millions of square kilometers. These eruptions formed the Central Atlantic Magmatic Province, one of the largest volcanic events in Earth's history. For centuries at a time, the skies darkened with ash, and the air filled with carbon dioxide and sulfur. Rain turned acidic, washing minerals and toxins into the ocean. The chemistry of seawater shifted again, disrupting shell formation for ammonites, corals, and other creatures that relied on calcium carbonate. The effect cascaded through every level of the food web. The ammonites, those ancient survivors of previous extinctions, began to decline. The smaller, more delicate species vanished first, leaving behind only a few robust forms. fish populations fluctuated wildly, their distribution breaking apart as temperatures rose unevenly across latitudes. The apex predators grew hungrier, their hunting grounds shrinking, their competition increasing. In some regions, the giants turned on smaller members of their own kind. Fossils from the end of the Triassic show bite marks on ichthyosaur bones that matched the teeth of other ichthyosaurs, evidence of starvation and desperation. The world above the ocean was changing too. On land, forests withered under drought and fire, rivers dried or shifted course, altering the flow of nutrients into the sea. The once stable coastline of Pangaea began to fracture, forming new basins and shallow seas. For marine life, these shifts created both opportunity and danger. New habitats opened, but they were unstable, prone to sudden collapse. The continuity that had sustained the Triassic ecosystems for so long was breaking down, piece by piece. The ocean itself grew darker. Sediments from volcanic ash and runoff clouded the water, reducing sunlight penetration. The plankton that depended on light began to decline, reducing oxygen production. This deepened the anoxia already creeping upward from below. In many places, the seafloor became a graveyard, a silent expanse of black mud where nothing stirred. The once busy reefs of the Tethys Sea turned pale and empty. Their builders, the corals and sponges, could not survive the combination of heat, acidity, and low oxygen. When they died, the intricate networks of life that depended on them collapsed. For the apex predators, survival became a matter of luck as much as adaptation. Some migrated to cooler waters near the poles, where oxygen levels remained higher. Others stayed and perished as their prey vanished. The ichthyosaurs, which had once ranged across every ocean, began to retreat into smaller populations. The plesiosaurs, with their flexible bodies and varied diets, fared slightly better, but even they struggled as the abundance that had once defined the Triassic seas disappeared. The end of the Triassic was not a single event, but a sequence, a chain of disruptions that built upon each other until the system could no longer recover. Each eruption, each pulse of carbon dioxide, each shift in current added to the strain. The planet warmed by several degrees, the oceans acidified, and entire ecosystems vanished within a few 100,000 years. It was not as total as the catastrophe that ended the Permian, but it was enough to reset the balance once again. Nearly half of all marine species disappeared, including many of the great predators that had ruled for so long. In the fossil record, this transition appears as a quiet line, a boundary where abundance gives way to scarcity. Above that line, the diversity of shells and bones diminishes sharply. The intricate ammonite forms give way to simpler, more uniform shapes. The coral fossils vanish almost entirely. The sediment layers grow darker and thicker, filled with carbon-rich material from decaying life. It is a geological obituary, written not in words but in texture and colour. Yet even in this collapse there were survivors. Some species of ammonites persisted, their simple shells proving more resistant to chemical change. Small fish adapted to new temperature ranges. Early relatives of modern turtles and crocodiles found ways to endure. The ichthyosaurs, though diminished, did not disappear. The plesiosaurs diversified again in the following epoch. The extinction was devastating but not final. As before, life retreated only to regroup. In the depths, the microbial world continued unbroken. Bacteria and archaea, feeding on sulfur and methane, thrived in the anoxic waters. They formed dense mats on the seafloor, their activity altering the chemistry of the ocean once more. From this invisible foundation, recovery would eventually begin. The ocean, though wounded, never stopped breathing. The aftermath of the collapse reshaped the planet. The breaking of Pangaea created new coastlines and shallow seas, fresh arenas for evolution. The climate, after its violent swing, began to stabilize. Over millions of years, the survivors diversified into new forms. The Jurassic seas that followed would host even greater giants, pliosaurs, mosasaurs, and other descendants of the Triassic lineages. The extinction had cleared the stage for a new cast. To imagine the final days of the Triassic seas is to picture a world both beautiful and strange. The surface might still have shimmered under the sun, the waves still rolled against the shores, but beneath them the silence had deepened. The reefs were gone, the schools of fish scattered. The great reptiles moved more slowly, their numbers dwindling. The water, once full of life, had become heavy with decay. Yet even then, in the stillness, there was the beginning of something else. Tiny plankton floating in the gloom, fragments of coral beginning to regrow, the faint stirrings of recovery. The ocean has never been destroyed, only transformed. Each extinction leaves space for something new, each loss a foundation for another beginning. The fall of the Triassic seas was not an end but a turning of the tide. The same processes that brought destruction, the shifting continents, the restless volcanoes, would also create the new worlds to come. The ocean would breathe again, and life, as it always had, would find its way back. When we look at the fossils of that era now, at the bones of ichthyosaurs entombed in limestone, at the delicate spirals of ammonites pressed into rock, we see not tragedy, but continuity. They are reminders that the sea is both fragile and eternal, capable of collapse, but never defeat. The Triassic giants are gone, but their descendants still swim in the patterns of sharks, dolphins, and whales. The reef builders have changed, but the reefs endure. The cycles that began in those ancient waters still turn with every tide today. If one could stand on a Triassic shore in those last days, the view would be deceptive. The sky would be bright, the horizon endless, the waves glittering in the sun. Yet beneath that surface lay the slow undoing of an age. The giants that had once ruled would soon vanish, their echoes fading into the sediment. But in the silence that followed, the sea was already dreaming of what would come next. The ocean that spreads across the planet today is not the same one that filled the basins of the Triassic world, and yet, in every movement of current and light, its memory persists. The shapes of continents have shifted, the chemistry of the water has changed, and the creatures that swim within it have evolved beyond recognition, but the rhythm remains. Beneath the modern waves, the same ancient processes still govern life. The pull of gravity, the flow of currents, the cycle of growth and decay. Every tide that rises and falls carries echoes of the seas that came before. If one could look through time instead of distance, the continuity would be unmistakable. The whales that glide through the deep now follow the same migratory patterns once traced by the ichthyosaurs. Their sleek bodies, sculpted for endurance and grace, are living testaments to the same evolutionary solutions the Triassic giants discovered long before. The flippers of a dolphin, the streamlined curve of a shark's body, the way light filters through the upper layers of the sea. All of it is a reflection of designs perfected hundreds of millions of years ago. The ocean forgets nothing. It only transforms. The creatures of the Triassic may be gone, but their presence lingers in the anatomy of their descendants and in the structure of the marine world itself. The food webs that sustain modern seas follow the same architecture that took shape after the Permian extinction and stabilized in the Triassic. Plankton still form the foundation, microscopic yet indispensable, converting sunlight into energy that feeds the vast machinery of life above. The same invisible communities that rebuilt the oceans then continue to sustain them now, drifting through every current, rising and sinking in an endless rhythm as old as the Earth itself. The great predators of the Triassic have no direct descendants, but their legacy is visible in the behaviour of every large marine hunter that came after. When a killer whale coordinates a hunt with its pod, or when a great white shark rises silently from the depths toward an unsuspecting seal, it is repeating patterns of motion that once belonged to other masters. The strategies of ambush, endurance, and cooperation are not inventions of intelligence but inheritances of survival. They began when reptiles first learned to read the ocean's movements and let evolution refine their instincts into precision. The reefs that colour the modern tropics are also built on lessons learned in those ancient waters. The corals of today are different species, built from different symbiotic relationships, but the concept of the reef, the living structure, both shelter and sustenance, was perfected long before mammals walked on land. The Triassic seas saw their first experiments in complex reef building after the devastation of the Permian, and the success of that recovery still shapes the biodiversity of our oceans. Every fish that finds refuge among coral branches, every crab that hides in the crevices of a reef wall, participates in a system that originated in a world long vanished but not forgotten. Even the seabed holds memories too deep for light to touch. In layers of sediment beneath the ocean floor lie the compressed remains of entire worlds. Each layer is a page in a book written without ink, recording temperature, chemistry, and catastrophe. Traces of Triassic carbon, fossilized shells, and mineralized bones rest in those ancient archives, undisturbed by time. They tell of warmth and famine, of abundance and extinction. When scientists drill into those layers today, what they retrieve is not just data, but a voice from the deep past, whispering reminders of what has come before and what could come again. The Earth's oceans have always been both destroyer and creator. The same forces that drowned species in anoxic depths also nurtured the survivors that rose to replace them. In the Triassic, as in the modern age, balance was never a fixed state, but negotiation between extremes, between oxygen and suffocation, warmth and cold, feast and famine. Every fluctuation of temperature, every shift in chemistry, tested life's ability to adapt. The same tests are happening now, under new circumstances but familiar patterns. The oceans of the present are warmer, more acidic, and increasingly unstable, echoing conditions that once ended eras and began new ones. To study the Triassic seas is to see the modern world reflected in deep time. The patterns of collapse and recovery that defined that age are written into our planet's DNA. The warming that triggered the end of the Triassic was not a sudden event, but a slow accumulation, a few degrees over thousands of years, enough to tip the balance of oxygen and temperature. Today, the same forces move faster, driven not by volcanic release but by human industry. The parallel is uncomfortable, yet instructive. The past is not a warning so much as a mirror, showing what happens when equilibrium is broken and how long it takes to mend. The modern ocean, vast and vibrant, hides its fragility behind abundance. Schools of fish stretch for kilometres, whales migrate across hemispheres, and coral reefs shimmer with life. But beneath the surface lies the same vulnerability that once unmade the Triassic world. Carbon accumulates again, temperatures rise, and oxygen levels in some regions fall. The anoxic zones that once crept upward from the Triassic depths are reappearing in the modern sea, slowly expanding along continental shelves. The story is not identical, but the echoes are unmistakable. The life that endures today carries the resilience of its ancestors. Every modern species is a survivor of countless extinctions, shaped by crises and recoveries. The ocean's inhabitants have adapted to extremes before, and they will again. Yet the scale of change determines the scope of recovery. In the Triassic, life rebuilt itself over millions of years. For the present, the timescale is far shorter, the pressure far greater. The lessons from the ancient ocean are clear. The planet will endure, but the shape of life upon it will never be the same. Still, there is something profoundly steady about the sea. No matter how many times it has changed, it always returns to motion. The same salt that once flowed through the veins of the Triassic tides still circulates today. The same forces that shaped the migration of ammonites now guide the paths of tuna and whales. Even the sound of the ocean, the deep low hum created by the movement of waves and the distant rumble of tectonic plates, is a constant that links every age. When one stands by the shore and listens, that sound is not new. It is ancient, layered with echoes of worlds long gone. The creatures of the Triassic are gone, but they left a kind of inheritance that transcends form. They taught life how to fill an empty world, how to build balance from chaos. After the greatest extinction in the Earth's history, they remade the ocean into a functioning system again. That act of restoration, more than their teeth or bones, is their legacy. Every living thing in the sea today, from the smallest plankton to the largest blue whale, depends on the architecture those ancient survivors rebuilt. The Triassic was not just an era of monsters. It was the moment the ocean learned how to live again. In the quiet depths of modern oceans, paleontologists have discovered entire graveyards of ichthyosaurs and plesiosaurs, their bones preserved in stone for over 200 million years. Some are so complete that even the outlines of soft tissue remain, shadowed impressions of fins and eyes. These fossils do not just reveal anatomy, they capture motion, posture, and behaviour. A mother ichthyosaur fossil found with embryos inside tells of live birth in the open sea. Another shows an individual caught mid-swim, its body curved in a final arc. These are not relics of monsters, but snapshots of lives lived according to the same laws that govern every creature today. Every fossil is a conversation between past and present. When scientists reconstruct an ancient predator from fragments of bone, they are not reviving a ghost but uncovering a continuity. The physics that governed a Triassic ocean, the density of water, the drag of a fin, the efficiency of a streamlined form, remain unchanged. The same equations still determine the speed of a shark or the glide of a whale. Evolution changes the players, but the rules stay the same. The ocean's game is eternal. Modern reefs, despite their brilliance, are vulnerable in ways the Triassic reefs once were. As temperatures climb and acidity increases, the calcium carbonate structures weaken, just as they did during the volcanic warming of the late Triassic. Coral bleaching events leave ghostly white frameworks where vibrant colonies once stood. Fish that depend on those reefs migrate elsewhere, disrupting entire ecosystems. It is the same story written in new water. The fall of one species opens the door for another, but the time it takes for balance to return stretches beyond the span of human perception. The deep ocean remains a mystery even now, just as it was to the creatures that rule the Triassic seas. Below 200 meters, where sunlight fades completely, the conditions resemble those that followed the ancient extinctions. Cold, dark and sparse, yet filled with life adapted to endurance. There are fish that create their own light, crustaceans that live among volcanic vents, and bacteria that feed on minerals rather than sunlight. They are descendants of the same microbial pioneers that repopulated the oceans after every collapse. In their resilience, one can still glimpse the persistence of the Triassic world. Every journey through deep time ends in reflection. The Triassic Ocean was a place of beginnings, not endings. It was the recovery of life's rhythm after silence, the rediscovery of balance after devastation. The creatures that filled it were both experiments and architects, shaping the blueprint of all that followed. The giants that swam through those waters did not just dominate their era, they set the pattern for what the ocean could become. Today, when we look into the blue and watch the silhouettes of whales rising through shafts of sunlight, we are seeing that same pattern continued. The language of motion, the grace of adaptation, the quiet intelligence of survival, all were first written in the seas of the Triassic. The ocean we know is not their descendant, but their continuation, a living memory carried forward in every tide. There will come a time when the modern ocean changes again, when the species we know become fossils of their own. But the rhythm beneath the waves will endure, as it always has. The sea will darken, then brighten, empty, then fill again. Life will retreat and return. The lessons of the Triassic are not only in the rocks, but in the resilience that still defines the water. The ocean story is unbroken, a single, endless current flowing through time. And somewhere, in the depths where no light reaches, the faint shimmer of life continues its work, rebuilding, adapting, remembering. The echoes beneath modern waves are not ghosts but promises, reminders that even in the face of change the sea endures, carrying within it the memory of every world it has ever been.